Everyone knows what a pendulum is. It swings back and forth, back and forth. The period, or time that the pendulum needs to return to the original position depends on just the length of the string and the acceleration due to gravity. Since the acceleration due to gravity is the same for all of these pendulum, it's the length that must be different. Let's look at the shortest string. This pendulum takes 60 oscillations per minute. Now, let's look at one with a longer string. This one makes 45 oscillations per minute. Now, let's start with an entire wave of pendulums together. Watch. Looks pretty cool, right? This mesmerizing pattern is just a result of different pendulum lengths. Instead of remaining staggered in this way, in about a minute all the pendulums will return to the same position. How does that happen? Well, we made the lengths of the string such that during 1 minute the shortest pendulum finishes 60 oscillations, the next one 59, the next 58, and so on and so forth. The longest pendulum does 45 oscillations per minute, so in 1 minute they should all return to their original position. And there you have it, they're all back in sync. The air around us is mostly nitrogen. So you can think of liquid nitrogen almost like liquid air. Does this mean that we can freeze air into a solid with liquid nitrogen? Obviously not, because the freezing temperature of nitrogen is lower than the temperature of liquid nitrogen. However, let's watch what happens when a glass of liquid nitrogen is put under a bell jar. Under this bell jar, a vacuum pump can suck out all the air in a matter of seconds. Watch as our once liquid nitrogen turns into a chunk of slushy ice. We just made solid air. But how did it happen? Evaporative cooling. This is what happens when you sweat on a hot day. The moisture evaporates off your skin and cools you down. When the liquid nitrogen boils, its fastest molecules leave the surface. Now, after we turn on the vacuum, we're taking away the fastest, most energetic nitrogen molecules, so this liquid cools down to the point where it turns into a solid. Look, I bet you thought you'd never see solid air. This is a slushy you could order on the freezing planet of Neptune. After the pressure is released, we can see that the solid nitrogen quickly returns to its liquid form. I like big bubbles and I cannot lie. Bubbles are always fun. Normally when you blow bubbles, they sink. Why is this? Gravity. Barring any other force, gravity brings the bubbles down. Now, let's blow bubbles into these two similar aquariums. The bubbles on the right float and don't sink, defying gravity. How does this happen? The difference is that it contains dry ice. This dry ice filled the aquarium with carbon dioxide. This phase transition from solid to gas is called sublimation. Carbon dioxide gas is denser than air, so it creates a buoyancy force pushing the bubbles up. This is similar to the force that makes a helium balloon fly up and away. However, as always, there is still gravity pulling the bubbles down. When these two forces balance, the bubbles float. Try this at home, but don't forget to take the fish out of the aquarium. If a 2-liter bottle is partially filled with liquid nitrogen and the cap is then sealed, will it explode? Nitrogen gas. At atmospheric pressure and room temperature, it occupies a 700 times larger volume than liquid nitrogen. Because the air around us is mainly nitrogen, we can see that the bottle must be weighted in order to be submerged. Even sealing a small amount of liquid nitrogen in this 2-liter bottle would be like expanding a basketball to the size of a house. Whoa! Let's see that again. Immediately after the liquid nitrogen is in the 2-liter container, the warm water begins to heat it up as it begins to transition back into its gaseous phase. At this time, the gas expands and expands until the walls of the 2-liter bottle cannot hold it up anymore. The result? This beautiful explosion. Now that we've seen what one bottle can do, we're going to go ahead and try a 5-barrel explosion. With 1,000 multicolored plastic balls. Imagine where all these plastic balls are going to go if the bottles are partially filled with liquid nitrogen and then submerged underneath them. Let's find out. Looks like the plastic balls went up along with the nitrogen gas that was stored in the bottles. Let's see that one last time.
Wouldn't it be cool if you could see in total darkness? We can using infrared light that is beyond what our human eyes can naturally see. Understanding this requires that we understand the nature of light itself. The light we see is just a portion of the spectrum of electromagnetic radiation. Electromagnetic radiation is a type of wave, like sound. Waves can be characterized by their length or frequency, with infrared radiation being longer than visual light. With their eyes, people can only see the visible light reflected from your body. In addition to this reflected light, our bodies and all other objects emit their own radiation like a light bulb. Its wavelength and intensity depends only on the temperature. Our bodies emit in the infrared, which has wavelengths longer than what our eyes can see. Notice how in this dark room, once we record seeing infrared light, everyone can be seen easily because people are hotter than their environment. This is how our snake was able to save the day, as they are one of the only few creatures that can see infrared light. Infrared light has longer wavelengths than visible light. Even though we can't detect it with our eyes, we interact with it every day as heat. This infrared light can also pass through certain materials, showing what is underneath. In addition to ruining some magic, being able to view infrared light is kind of like having a superpower. You could speed up search and rescue efforts. You could diagnose fevers and burns. You could stop phone batteries from exploding. You could write secret messages in heat ink. And most importantly, you could put a halt to pizza burns forever. Today, we're making a cloud in a bottle. Most of us are familiar with how clouds are formed. Even though we understand this, we can't regulate the weather. Outside of comic books, scientists haven't had much success with controlling the weather. As scientists, we know that high and low pressure areas cause the everyday changes in our weather. But on small scales, we can create our own clouds using this little bottle. First things first, our demonstrator will add rubbing alcohol to this bottle. Imagine the air in the bottle as our atmosphere and the alcohol as Earth's water. We're going to pressurize the bottle by pumping air into it with this bike pump. Watch how with the simple power of pressure, we can evaporate the alcohol into a cloud and condense it again. Making clouds is quite the workout. Once we've added enough air, we can cause a sudden pressure drop by popping the stopper off. There it is, a cloud in a bottle. The sudden pressure change caused the alcohol to quickly evaporate. This causes rapid cooling, transforming the alcohol into a cloud. Now, as we pressurize the bottle again, we see the cloud slowly precipitate back into a liquid alcohol at the bottom of the bottle. We can continue the cycle as many times as we want. If we pop the stopper again, the cloud comes back. This is a lot like how the real water cycle works. As long as water stays on planet Earth, the cycle keeps going wherever there is a change in pressure. Let's start by handing off a wheel that is spinning and one that is not spinning to a person on a freely rotating platform. What will happen if they flip the wheel? Wow! The guy on the right started turning! This is because he flipped the wheel, making it spin in the other direction. Physics forced him to automatically rotate to compensate, thus preserving angular momentum. The guy on the left? No spin? No spin. Imagine you're on a spaceship. Rocket fuel costs a lot. How do you change the direction of your spaceship? Use a bike wheel, or any rapidly rotating disc. We call them gyroscopes. Let's look back at why the bike wheel didn't fall off the rope when it was spinning. When the wheel is spinning, the force of gravity can't make it fall. Instead, it creates a torque which makes it rotate around the rope. We call this motion precession. Our Earth is just a giant spinning body like the disc. The gravity of the sun and moon represented by the weights causes the Earth's axis to precess. This precession is very slow, with a period of 26,000 years. As we speak, the North Celestial Pole is moving slowly away from the North Star. Eventually, the North Star won't reliably take people north anymore.
This is the sound of a Tesla coil. This is the sight of a Tesla coil. The Tesla coil is a concept built on electricity and magnetism. This device is over 6 feet tall, and the round silver part on top is called a toroid. Although this is where the action occurs, it's not the most important part of the coil. Our Tesla coil can output over 1.8 million volts of electricity and 3 milliamps of current as it strikes into the air. This power could charge your phone in only a few seconds. How can this device be plugged into the wall and yet create these huge bolts of electricity? This is where magnetism plays its part. As the primary coil receives electricity, it creates a magnetic field inside the secondary coil of wire without touching it, which allows for a huge step up in voltage until it reaches the top of the toroid. This enormous amount of electricity then creates arcs in order to find the fastest route back into the ground. In this case, although somewhat hard to believe for some, the closest path to the ground is in fact through the building. What do you think will happen if we set up a traditional fluorescent light bulb only near the coil? Will it light up without any mounting or plug? How cool is that? The electricity can travel through the air to power the light bulb. Let's watch this beautiful display of electromagnetism one more time. Oh no! Watch out! How is this ordinary magnet defying gravity? It's levitating on an extraordinary material called a superconductor. A magnet approaching a conductor causes electric currents to be generated in the conductor, which create a force slowing down the magnet. Unfortunately, currents die off quickly because of an electric resistance in the conductive materials. However, the resistance of some materials drops to zero at low temperatures, causing them to levitate. These materials are superconductors. Here we have our superconductors. They are just ordinary pieces of ceramics at room temperature. But when cooled down to liquid nitrogen temperatures, they become phenomenal. At this temperature, they lose all resistance. This keeps currents from dying off, allowing superconductors to become suspended. Moreover, the magnetic flux penetrating into a superconductor keeps it at a fixed distance from the magnet, preventing it from falling. But unless we can keep them consistently cold, they lose their superconducting abilities. So, we build reservoirs for our superconductors to keep them cold. Even then, it's difficult to keep them cold. If somebody finds a material that is superconducting at room temperature, it'll be a major breakthrough. Note how the magnetic flux pins a superconductor to a roller coaster magnetic track, forcing it to follow the track at a fixed distance from its surface. It doesn't even fall when you flip it over. Imagine superconducting cars or trains levitating above or below magnetic tracks, with air resistance being the only thing restricting movement. Superconductors open up the possibility for endless creativity and innovation if we can find one that operates at room temperature. So get out there and help us find one. Not many sounds beat the crack of a baseball bat hitting the ball. But have you ever wondered why some hits sound differently than others? The answer is, of course, physics, specifically acoustics and vibrations.
think of a guitar string. When the string is plucked, it vibrates back and forth really fast between its two fixed ends. This vibration compresses the air, generating sound. When a guitar is properly tuned, a harmonic sound is produced, which is pleasing to the ear. This same principle is behind the sound a bat makes when hitting a ball. When a bat strikes a ball, the bat will vibrate with the batter's hands and the point where the bat meets the ball. These are our fixed points, much like the guitar string. It's this vibration that makes your hand sting after hitting the batting cage. Did you hear that? That's the sound of a well-struck ball. Let's take a closer look at where the bat strikes the ball. See this spot? That's called the sweet spot of the bat. This is the best place to hit a baseball if you want it to go far. It also happens to be the place for a really good sound. Because of the structure of the baseball bat, the sweet spot produces a vibration, shaking back and forth roughly 170 times a second, producing a harmonic tone. It also transfers the largest amount of energy to the ball. If you hit a baseball somewhere else in the bat, you'll hear a different tone. Experienced baseball players know when they need to back up or go forward based on just the sound of their hit. So the next time you're at a baseball game, enjoy the sweet sounds of vibrational physics.
This is our giant magnifying glass. It's called a Fresnel lens and was originally designed for use in lighthouses. But it's far more fun to use to burn things. You'll notice that our lens isn't shaped like a magnifying glass, but it's actually made from an old TV screen. If you find an old TV somebody threw out or at a yard sale or thrift store, you could build your own heat ray. Fresnel lens with the screen. The screen isn't made of glass, and it's flat. If you look closely at the screen, you can see that there are ridges that form concentric circles. These concentric circles are what magnify the light as it goes through the lens. Enough talk. Let's set things on fire. This demonstration is dangerous and should never be done without proper safety equipment. Let's start with this wooden stake. To get the wood to burn, we need to find the focal point. This is where the sun's energy is focused onto a single point. When the wood meets the focal point, it can scorch and catch on fire very quickly. This is one demonstration of the power of the sun and the Fresnel lens. Let's burn a few more things. Let's see what happens with this plain white sheet of paper. Bam! No match for our death ray. Fresnel lens. By melting wax crayons, we can create some abstract modern art. When art and science come together, the results can really be colorful. You can even make yourself some food by focusing the sun's rays. I guess that's one way to cook breakfast. Yum. Submitted for your approval, an ordinary racquetball. Or is it? Watch as we demonstrate the effects of the extreme cold of liquid nitrogen. What made a traditionally rubber racquetball lose its bouncing properties? Oddly enough, the answer is all around us. In fact, it makes up 78% of the air we breathe. Liquid nitrogen, at about 400 degrees colder than your average indoor temperature. Dunking a racquetball into a substance this cold makes the softest and most flexible of objects rigid and brittle. Since it evaporates so quickly, even pouring out this liquid doesn't cause a mess. What do you think will happen to these flowers when frozen in liquid nitrogen? Instead of shattering these flowers, what would happen if we just allowed them to thaw out? As you can see, the flowers are not in the same condition as they were before. Perhaps that'll give you a second thought before ever allowing yourself to be frozen. This tank of methane is connected to a bucket that is filled with the soap water and glycerin solution. The methane is pumped through the copper pipe into the bottom of the bucket. This pumping action into the liquid creates bubbles that are filled with pure methane. We can tell that these bubbles are filled with methane because if you let some of the bubbles loose, they'll begin to float up because methane itself is lighter than the air around us, which contains mostly nitrogen. This very property of methane allows us to create a tall pillar of bubbles without worrying about it falling over. Now, methane is a very flammable gas. You'd know this if you lit a candle behind a cow. If you haven't, don't. This is the very reason why our demonstrator is wearing a flame retardant jacket and safety goggles. Because methane is very flammable, we don't want to just release these bubbles. That would be dangerous. So, let's dispose of them. Impressive. Now, for something potentially very dangerous. We've shown you that methane is a very flammable gas. Do you think it would be safe for our demonstrator to scoop a handful of the bubbles and light them on fire? Mind you, while still holding them. Like many things, there's only one way to find out. And it looks like our demonstrator's hand is completely fine. But how? If you paid close attention, before our demonstrator grabbed the bubbles, they drenched their hand in water. This coated the hand and created a barrier of moisture. When the fire was lit, the water on the hand was vaporized, thus creating a layer of steam that protected the hand for a split second. That split second is long enough to prevent any harm to their hand. Remember, you should never try this at home.
Howdy, and welcome to the 2022 Physics and Engineering Festival, hosted by Texas A&M University's Physics and Astronomy Department. I'm your host, Morgan Nasser. We have a great lineup of science demonstrations today that will make anyone smile, regardless of age. But first, we would like to thank our amazing donors Halliburton, Ralph and Marcia Schilling, Class of 68, Nancy and Robert Dunham, Class of 63, Inlight Technology, Colonel Hal Shade, Class of 67, and Ramiro Galindo, Class of 60, for making this year's festival better than we could have imagined. If you like what you see today, don't be shy about hitting that big subscribe button. This means a lot to us as we grow our channel, release more content, and more. Also, be sure not to miss a chance to win a bundle of science goodies such as a glow-in-the-dark frisbee, skyhook, diffraction glasses, and more. Simply go to tx.ag/science giveaway. There's a link for that on screen and in the video description. And with that, let's get into our schedule. Today, we'll showcase some truly spectacular physics demonstrations like a balloon race, dry ice bubbles, imploding drum, ping pong cannon, bed of nails, Bernoulli's principle, and much more. If you have any physics questions, please ask them. We have a panel of experts in the chat ready to answer. And if you ask an especially unique question, we may answer it here in our studio. At 11 a.m. Central, we'll have our first keynote speaker, Dr. Nancy Curie-Gregg, a NASA astronaut with over 1,000 hours in space and professor of engineering practice here at Texas A&M University, presenting her inaugural Dr. James G. Potter Lecture. Following her talk, we'll give everybody the opportunity to ask any question with a distinguished faculty member, scientists, and demos in our Zoom rooms. A link for that will be presented later on screen. After that, if you don't want to miss our grand finale, after that, you don't want to miss our grand finale, a 5-barrel depth charge explosion. Watch out for the splash zone. And last but not least, don't miss our second keynote speaker, Alex Filippenko, giving his Mitchell Lecture at 3 p.m. Central. He is a professor of astronomy at UC Berkeley and award-winning author and winner of the 2004 Carl Sagan Prize for Science Popularization. Now, are y'all ready to have an especially good time? Great! Then let's get started with the one, the only, Dr. Tatiana.
Hi, Morgan. That was too much, but thank you. Now, I have a very special experiment for you, one of my favorite experiments. Look, I have this balloon here, nice maroon, Applied with Physics, Texas A&M. And here I have liquid nitrogen. Liquid nitrogen is a very cold liquid. It is a temperature that is 400 Fahrenheit, colder than temperature of your skin. You have to be very careful when you work with liquid nitrogen. Now, if I put liquid nitrogen on this balloon, what will happen? Well, it's shrinking. And we understand why. Because when I cool it down, motion of molecule slows down, pressure drops, and balloon shrinks. Now it's coming back when it warms up. Well, great. Now, I have even more interesting experiment for you. I'll have a balloon race. 2 balloons. One, well, it's orange. But another one is maroon. Carl, Texas A&M. Fly with Physics, Texas A&M. Question for you. If I pour liquid nitrogen on both balloons, which one will shrink first? Which one will win? Orange or maroon? Ready, set, go! Look at this. Maroon shrinks to nothing. I can pour nitrogen on this one. There is still some amount of air inside orange. Maroon wins. Why? Well, I put different gas inside these 2 balloons. What did I put inside this one? Air, which is mostly nitrogen. What did I put inside maroon balloons? Oxygen. And boiling temperature for oxygen is a little bit higher than for nitrogen. I want people to convert all oxygen inside this balloon to liquid oxygen. You know what? Maroon wins.
Howdy, everyone. This demonstration will take around 2 or 3 minutes, so I'm gonna start it off ahead of time. Let me do that right now. Over here I have a steel drum that's normally used to transport oil from location to location. What I'm doing right now is actually evacuating it, taking out all the air from the inside and having all the air from the outside, which is due to the atmospheric pressure, try to contract as much as possible. This is basically a huge example of a water bottle. No, don't worry, that's not it. Let me show you guys how much force the atmospheric pressure can actually act on you at all times. So it's around 15 pounds per square inch. Let me show you guys real quick. Oh boy. Okay, so I took out all the water and all the air out of this bottle, and what happened was that it contracted. It wasn't due to me, it was due to the atmospheric pressure actually putting a lot of force on the outside because I had no air in the inside, which means I had no force on the inside to counterbalance that overall force of the atmospheric pressure. So what's gonna happen here is basically the same thing on this can, and we'll have to wait maybe a couple more seconds to see the aftermath. But while we wait, I'm gonna go over again how much force, oh my God, I'm not ready for this. How much force the atmosphere is actually acting on you all the times. Again, it's around 15 pounds per square inch. It's a lot of force on you all the times that can actually normally do a lot of damage, but our bodies actually evolved to deal with that. All of our water, all of our blood, all of our bones and muscles are counterbalancing that sheer amount of pressure. So we can actually survive on a daily lives. But what would happen if we actually, again, got rid of all that stuff inside of us? Well, let's watch and see. Oh my God, how long it's gonna take? Let's see, 3, 2, 1. Anybody? We're all waiting? Okay, well, now we're here. Let's see how long this takes. Oh, I felt that, even right here. So basically what happened after it imploded was that the sheer amount of force that this thing used to contract actually pushed all the air in towards my direction, basically pushing me back slightly as well. Well, here we go. This is exactly what happened to my water bottle, and I used that to basically contract the steel drum. All right, thank you guys, and Gig'em. Oh my God. That took...
Howdy everyone, thank you so much for joining our Physics and Engineering Festival today. Today, me and Carly are going to show you one of our favorite demonstrations, skyhooks. Okay, are you ready, Carly? I'm ready. I'm going to need your finger. Okay, I want you to balance this right on your finger. Do you think you can do it? Yeah. Okay, concentrate. Do you guys think she can do it? Okay. Oh, I already practiced this. I know. Okay, it's okay. We're physics majors. We're going to try again. Okay, I'm going to add this really heavy belt to it. Wait, we're adding more mass? Yeah, you can do it. Okay, yeah, I promise. It'll be fine. It'll be fine. You ready? You focused? Yes. Really, really focused? She did it! How did she do it? So what we did when we added this belt is we changed the center of mass from being at the tip to being underneath her fingertip, right where this belt buckle is. So now it's super easy for her to do it, or hold it. So give us a little spin. And you can even make demonstrations like this at home. Here I just have a cork with a screw put in at the bottom. And if I put a fork here in the screw, 1, 2. This is all about just the center of mass of the object that you're holding. Super fun demonstration that you can impress anyone at home with. Thank you guys so much for joining us right now.
Howdy everyone. So last year, if you attended our festival, you may have seen a demonstration on Lenz's Law, which I like to call the Lenz's Law race. And in that demonstration, you saw objects, magnets, that were falling at different rates depending upon what material they were attached to. So there was an aluminum tube, and as you may recall from that demonstration, aluminum is not a magnetic material. So if I have a magnet and I put it anywhere near this aluminum ring, nothing's going to happen. However, if I put this aluminum ring over this pipe, what we have here is a solenoid. And when I push this button, there's going to be a current which is generated in this solenoid, which is going to create a magnetic field. That magnetic field is going to pass through the ring, and nature is going to oppose that magnetic field by generating a current in the ring. And let's find out what happens. Ready? 3, 2, 1, go. So you see how the ring jumps. Now, this is basically the same aluminum ring. The only difference is, if you can see it, there's this little slit which is inside of it. So when I put the ring here and press the button, nothing happens because currents can't be generated, and thus it doesn't jump. So what I want to show next are 2 other aluminum rings, but there's a big difference between these two. They have the same diameter, they're the same material, but you notice that the thicknesses are different, and thus the masses are different. So what I want you to do in chat right now, I want you to go ahead and make a guess, make a prediction. Which one do you think is going to jump higher, the thin ring or the thick ring? All right, ready? I'm going to go ahead and put the thicker ring on this. I'm going to press the button. Let's see which one goes higher. All right, so you saw where the thick ring went, right? Hopefully you caught that. Now I'm going to go ahead and put the thin ring. Ready? 3, 2, 1, go. So you notice that the thin ring did not go as nearly as high as the thick ring. And we might think that the thin ring should go higher. Why? Because it's less massive than the thick ring. But nature has this thing called resistance. And resistance is essentially a product of numerous factors, one of which is the material, another which is what we call the cross-sectional area, the area that the current has to pass through. So the thin ring has a smaller cross-sectional area than the thick ring. The result is that it is harder to pass current through the thin ring than the thick ring. But before I leave you, I want to show you something even cooler. LN2 cool. So I'm going to put these goggles on for safety and these gloves. Well, this glove. And I'm going to go ahead and take a ring and stick it in liquid nitrogen to cool. Now, I'm going to go ahead and pre-cool some, which I've already done, and I'm going to show the same thing. I'm going to go ahead and take a thick ring and a thin ring and cause them to jump. Now, make a prediction. Which one do you think is going to go higher, the thin ring or the thick ring? Ready? 3, 2, 1, go. So the thin ring almost touched the ceiling. Sorry, the thick ring almost touched the ceiling. Now I'm going to go ahead and get the thin ring. All right, ready? 3, 2, 1, go. So I don't know if you could see that, but it actually hit the ceiling. So now there's really no difference between the two heights that they reached. It was very negligible. Why? Because when we cool it down to liquid nitrogen temperatures, the resistance essentially becomes very negligible in both by comparison to what it was before. So the masses and their effects of the mass don't have as much of an impact. So I hope you enjoyed this demonstration, and I hope you enjoy the rest of the festival. Have a good one and gig 'em, guys.
Go. Howdy, everyone. Thank you for joining me today with Dry Ice Bubbles. Believe it or not, this is a demonstration that you can actually do at home. Just make sure you wear protective gloves when working with dry ice. It's very cold. So here I have 3 cups filled with dry ice, and I'm going to add water to increase evaporation. Now I'm going to take this napkin and I'm going to dip it in a bubble solution. And I'm going to drag it across the top of these cups. As the pressure is building up inside these cups due to evaporation, it's pressing against the top of these soapy films and causing bubbles. Thanks for joining me today. Enjoy the rest of the festival.
Oh, hello there, and howdy. I have a question for everyone. Where is it easier to swim? The swimming pool or the ocean? Well, we're going to find out right here, right now. Here I have regular soda and diet soda. The diet soda has a sugar replacement called aspartame. You need a lot less sugar in this diet soda than you would in a regular soda can. And because of that, we actually have a difference in density. Let's show you what that causes in water. Let me have this regular soda in the water, and it sinks. Now we have this diet soda in the water, and it floats. This is because the relative density between the two soda cans actually differs in the water. One is less dense than the water and it floats. One is more dense than the water, so it sinks. But in the ocean, we actually have a lot of salt, which actually increases the density of the water. And let's see the actual effect of that. So slowly but surely, we dip some salt here, here, and there. As you can see, the regular soda actually starts to float just like that. This is why you can actually swim and float a lot easier in the ocean than you can in a swimming pool. Thank you.
So what we have here is our Coriolis carousel. This is a demonstration on how the rotation of the Earth affects the perceived trajectory of objects. So what you see in front of us is Nicole and Carly. They're just passing a ball back and forth. And to get the ball to go from one to the other, they just toss it in a straight line, exactly at the other one. But the moment that we get them to start to move and rotate, it becomes a lot harder for them to hit the actual target. So why is it suddenly so much more difficult? The reason is that this rotation causes the ball, from their perspective, to essentially move off to the right. And so I want to show you that kind of view real quick. So, and as we can see, it becomes much harder for Nicole. Here. Becomes much harder for Nicole to get the ball to reach Carly. This is a demonstration on why when we see long-distance projectiles, the bullet seems to fly off to the right due to the experience of the rotation of the Earth. Have a great time at the festival, everybody. Let's go!
Howdy! I have a very interesting experiment for you. Look, I have a challenge. I have this long balloon, and I have this little flask. Can I fit this long balloon into this little flask? Can I do that? No, I cannot. But you know what I have to do. I have to cool it down, right? What I have here is liquid nitrogen at temperature that is negative 196 Celsius or negative 322 Fahrenheit. If I pour liquid nitrogen in this small flask, and then I will put my balloon in this little flask, look at this! It's shrinking! It's shrinking! Where does it go? It's shrinking because I cool it down. Motion of molecules slow down. Pressure drops. And we did it. The balloon is in. Now, what will happen if I take it out? Ready? Let's do it. I take it out. Balloon, where are you? Please don't let me down. Please don't let me down. Yellow balloon, yellow glove. Can you see? Don't let me down. Please come back. You never give up. One more. And I need large dior. If somebody can bring me large dior, that would be great. So, we never give up. We do it again. It is behind me. I'm shrinking this balloon again. It is coming. It is shrinking. It is shrinking. It is shrinking. White neck dior is there. And out. We never give up. We never give up. It will come back. I promise. At some point. Look at this. It's coming back. Thank you so much, Dawson. Really, what you can do, you can make your favorite balloon animals. My favorite is a giraffe. So, I'm making a giraffe for you. Almost there. Neck. Legs. Tail. No, second leg first. Tail is here. Giraffe is ready. Now I have to put my gloves on. And I have this dior with liquid nitrogen. We put the giraffe in liquid nitrogen. It is shrinking. But now, look, I take it out. What will happen? Giraffe, will you come back? Please come back. Please come back. Please come back. Okay, look at this. Ears are back. Nose there. Now, we need just a little bit of surgery. And the surgery is done. The giraffe is back. We did it. Thank you for joining us today.
liquid nitrogen is super cool, super fun, but super dangerous. So we have to be careful and wear our goggles. Here we go. And also our gloves. Let's not forget that. Okay. So liquid nitrogen reaches temperatures of a negative 322 degrees Fahrenheit. It is so cold that when it touches a hard surface, it basically instantly evaporates, just like that. And when it does, it increases in volume by 700 times its size. So let's use that to have some fun here. Here I have a device called a liquid nitrogen cork popper. I'm gonna pour some liquid nitrogen inside, just like so. What's gonna happen is the element 2 is gonna evaporate and go from a liquid to a gas and increase in its volume. Next, I'm gonna taper it off the top, close it up, and eventually the liquid nitrogen will evaporate, increase the size, and reach a certain threshold that it will actually push the cork out. Now watch. 3, 2, 1. Just wait. You can hear it. Oh my God. Just like that. I just caught it. Let's do that one more time to show you the sheer power of liquid nitrogen. Okay, a little bit more. I'm gonna do this one at an angle, shoot it after the crowd. There's no crowd here, don't worry. Wow, that went super far. As you can see, you can do crazy things with liquid nitrogen. It is very fun, but again, leave it to the professionals. Thank you, everyone.
Wow, I wish we could start every day with science demonstrations. You've all been asking wonderful questions, so let's dig into those now. For our first expert, let's have Dr. Welch. One moment, please. For our first expert, we have Ryan Mueller.
Hey everyone. So I think there's a question on how many different types of dark matter particles are there in the universe? That's a really interesting question, and it's kind of hard to answer because, I mean, we don't know. We don't know what dark matter is at all. So it's probable that dark matter exists. It's probable there are particles out there, but we don't know. However, I can tell you that there are different categories of dark matter hypotheses that we search for that have different amounts. For example, the most common ones looking for what we call WIMPs, or weakly interactive massive particles, only look for primarily one dark matter candidate. These sorts of models, we say, okay, there's all these new particles, and maybe one of these particles is a dark matter candidate. So there's only one, and it explains everything. More recently, other theories have been proposed that say stuff like, maybe there's a whole hierarchy of very heavy to light dark matters. What would this look like? And it turns out that if you do this, you actually end up seeing that you can explain different things that we see in the universe using these like hierarchical dark matter models. But the answer at the current moment is that we don't know, and I think it's a very good question because it really gets to the heart of the issue of why don't we know, and what is this stuff? And so hopefully in the next few decades we'll actually have a good answer to that.
Wow. Thank you so much. For our next expert, we have Dr. Welch here.
You ready to go? There was a question on TikTok that said, how do projectors project the color black? What a great question. You know, the answer is that they don't. You weren't expecting that, were you? Because everybody sees black on the screen. But black is where there's the absence of light. So projectors project light, and if they want there to be a place where there's no light, they just simply don't project any light on that point. And it looks black because there's no light going there.
Wow. Is that true for like television screens and whatnot too?
Sure, yeah. Yeah, and in fact, you know, technology goes in to trying to make the screens blacker because if you have the ability to project light, some of it might leak through. So even when you don't want any light, a little bit might be getting through, making it kind of gray. And you can pay a lot of money for screens where the black is the blackest.
Wow. Wow.
Yeah.
All right. Well, thank you so much, Dr. Welch. For our next expert, we have Dr. Bellianen here.
Hi everyone. So there was an interesting question on TikTok. What kind of jobs take physics? And contrary to popular belief that you only can be a physics teacher or a professor, actually, amazingly, most of jobs from high tech to finance take physics. Physicists work in national labs across all kinds of industries, in finance, especially in quantitative finance, anywhere where you would need quick analytic thinking and the ability to solve problems of any kind, physicists are employed. So you can learn more at the American Institute of Physics Statistics. When you just type aip.org, there will be plenty of statistics where the physics graduates go. Thank you.
I should remember some of that stuff. Good. Thank you. And let's see, for our next expert, we have Dr. Welch again. Welcome back.
Thank you. A couple of questions, actually. I mean, totally unrelated, but I see them coming in. I brought my computer with me to try to help, so I hope you don't mind. But one question is there more than one dimension in the universe? And, I think it depends on exactly what you mean, but to a physicist, the answer is, well, yes, there's at least three, okay, or even four. We live in a three-dimensional world, with height, depth, and breadth. So you can just take that as three to begin with. And the way our mathematical equations work, time works in these equations the same way those dimensions do. So in our math, we typically treat a four-dimensional world. Now, there are theories that there are even more dimensions that are very hard for us to access because they're curled up very tightly. That's known as string theory, and people have heard of that. It's still speculative. No evidence for these higher dimensions yet. Nothing's been found. The math works, but until an experiment shows it, it's still speculative.
Very cool. Now, you mentioned time as the fourth dimension. Can you go backwards in it?
Well, can I? No.
Can I?
No, you can't. The motion in time is something that's actually undergoing current research. I mean, people think that this is simply the evolution of complexity that is the reason why we appear, to experiencing, that we don't go back in time because. But that's again a hard question. Mm-hmm. Right, that's who's next.
All righty. And for our second expert, we have Dr. Belyanin.
Hi everyone again. So there was a question, why does the sky change colors throughout the day? It's all about scattering of the sunlight. So it turns out that particles in the air, from molecules to dust to aerosols to droplets, they all scatter sunlight. And it turns out that for really small particles, the blue light is scattered much stronger than yellow and red light. And therefore, during the day when there is just no cloud, sky is completely blue. What you see is this enhanced scattering of blue light by the very small essentially molecules in the air. However, at the sunset or sunrise, the light goes through a much larger depth of the atmosphere because it's kind of going through the whole, it's kind of going along the atmosphere, along the surface of the Earth. And as a result, the blue light is completely scattered out, and what you see is yellow and red. Now you may ask a question, what happens with the clouds? Why they are so gray or whitish? Well, they have a lot of water droplets, and those scatter more or less all colors uniformly. That's why you are getting this kind of dull gray color. Thank you.
Thanks so much. And once again, Dr. Welsh.
Not trying to hog the camera, but I just saw a great question on the chat that said, can anything in the universe reach 0 degrees Kelvin? And too long didn't read, answer is no. But if you want to know more about that, temperature is a measure of motion, of how molecules in a material are moving. But as you try to cool things, I mean, there's a principle that sort of the rate at which you can remove energy depends on the temperature difference. So as you get something closer and closer to 0 degrees Kelvin, you really can't cool it. And so the answer is no, you really can't get to 0 degrees Kelvin. You can get arbitrarily close, and people have done that. The lowest temperatures ever reached are well below a billionth of a degree, so 1 nanokelvin or less. But reaching 0 can't be done. And there's even a principle called the third law of thermodynamics that says you can't actually reach 0 degrees Kelvin.
From like a procedural point of view, so barring the explanation that you just gave, can something be 0?
Well, no, there's no way to get something to 0 degrees Kelvin. It can't be done.
I see.
But at some point, temperature can lose its meaning, especially if you have a very small sample. Temperature is an average. It's a representation of an average. And when you talk about an average, that means that you have a large amount of stuff, a large amount of molecules. And in anything that you deal with in everyday life, the number of molecules is very, very huge. But if you want to talk about a tiny sample where maybe there are only 100 molecules, well then yeah, temperature starts to lose its meaning, and people can play games with that. But as long as temperature has its meaning, then no, you can't reach all the way to zero. You can get real close, but you can't reach zero.
Very neat. Or should I say, cool.
Very cool, yeah.
All right. And with that, we'll close the first Q&A session. Remember, keep asking those physics questions in the chat. We have a panel of experts, and we may answer it here in our studio. Also, be sure to subscribe to our channel if you like what you've seen so far. After this next round of demos, we'll have our first speaker, Dr. Nancy Curie-Gregg, live at 11 a.m. Central Time. And with that, it's high time we stop making you wait. Let's get into those second round of demos.
This is my favorite demonstration. We will have loudest phase transition. I will take this bottle, Coke bottle. I will fill it with liquid nitrogen. I will close it, I will seal it, and I will put it in this barrel with water. What will happen? Liquid nitrogen will warm up. It will evaporate, turn into gas. And nitrogen as gas takes up 700 times more volume. Let's do it. Liquid nitrogen goes into the bottle. Now we close it, we seal it. And it goes into the barrel with water. Did you get it? Something else?
This other one wasn't working. Nope, that will do it. Howdy. I'm here to teach you about the force, the electromagnetic force. Oops, helps if I turn it on. Hi everyone, what I have for you today is a plasma globe. This is a common toy that can be purchased in many stores and online. And what makes it so neat is that when you turn it on, you see all of these really beautiful streaks of light that come from the center to the outer portion. A plasma globe is made up of a portion of noble gases that are inside of the globe and this little mini Tesla coil which creates a high frequency electromagnetic wave which permeates space. But what makes this even more cool is when you take a fluorescent tube and bring it near the plasma globe. Now notice that the tube is not connected to any power source. It's completely disconnected from any electricity. So is it possible to turn this on? Well, let's find out. So I bring it close and watch how the globe turns the light bulb on. What's really neat is why. The electromagnetic wave creates electrons which are then able to move through the tube and excite the inside mercury atoms, which then fluoresce and create the light inside of the tube. But pay attention to something. If I bring the tube close to the globe again, notice where the light gets cut off. Right now it's going all the way to the end of the fluorescent tube. But when I bring it and touch it at the center, notice how it dims. It gets significantly dimmer than it was before. So the reason has to do with the current that is generated. The current that is generated is being grounded by me to the ground. So the current doesn't pass all the way through the tube. I hope you enjoy this demo. Light is a lot of fun, and have a great time at the festival.
Howdy! I have a question for y'all. Do you think that I can throw this ball fast enough to go through this can? Well, probably not. As soon as I let go of the ball, the air around it starts to act against the ball and reduces its speed significantly before it even reaches the target. And we call this term air resistance. But what do you think would happen if we didn't have air resistance? Well, first of all, we'd be in really trouble, but we can achieve this with this ping pong cannon. And so basically all it consists of is a plastic tube with a ball inside. And on both ends is covered by this material called Mylar. Mylar is the exact same material used in emergency blankets. So what I'm going to do is once the Mylar is sealed on both sides, I'm going to turn on this vacuum and it's going to take out the air on the inside. Once this gauge says that I have reached a vacuum, I'm going to puncture a hole in the very end right over here. Once I do that, air begins to rush in from this side, and due to the force of atmospheric pressure, the force that we experience in everyday life, it'll lift up the ball and it'll travel along this way. And because we turned on the vacuum in the very beginning, we've greatly reduced the air resistance within the tube, and so it'll keep on accelerating until it bursts through the very end and into our cans. All right, let's do this. Safety first. I'm going to turn on the vacuum. So, in the chat, how many cans do you think this ping pong ball will go through? 1, 2, or 3? Let us know. All right, this may take a little bit. All right, let's go. So, 3. On the count of 3. 3, 2, 1. Woo! So it looks like the ping pong ball obliterated through 2 cans. If you said that in the chat, thank you. All right, thanks, Gig'em.
This is a demonstration on the Leidenfrost effect that we want to share with you. I have liquid nitrogen in this flask. This is a dangerous liquid. It boils at temperature negative 196 Celsius or negative 322 Fahrenheit. So if I ask you, is that okay if I put my finger in this liquid? You'll think that I do something really, really wrong. However, if we know physics, let's think about it. When I put my finger in for a short period of time, what will happen? There is enormous difference in temperature between my skin and liquid nitrogen. So liquid nitrogen will start evaporating vigorously around my finger, and it will create cushion of nitrogen vapor that will protect me, but just for a second. Let's check. Are you ready? 3, 2, 1. Ah! Nothing. I'm just fine if I do it for a very short period of time because of the Leidenfrost effect.
Enough with the cool stuff. I'm here to bring the fire. So what I have inside of this bucket are bubbles. Bubbles filled with methane. And methane, as you may know, is a very flammable gas. So you'd probably think I'm crazy to go ahead and light my hand on fire. But notice my hand is perfectly fine. Why is my hand fine? The same reason that Dr. Tatiana's hand was fine, the Leidenfrost effect. If you were able to see, when I stuck my hand inside of the bucket, I didn't just pull my hand out with bubbles. I actually coated it in water. So when I turned on the lighter and lit the bubbles on fire, my hand was protected for a fraction of a second due to a vapor layer being created between my hand and the flame. So everyone, don't do this at home, but let's light it up and enjoy the festival.
Howdy everyone. Today we're going to learn about pressure, which relates basically the force to the area, or first force per area. Over here we have 3 beds of nails that change in density of how much nails they have on them. So over here we have a lot of nails, then we go down, we have a little bit less nails, and down here is our least dense one. So when you have more nails on a bed of nails like so, you have less force per area. So what I can do here is actually test that out with a balloon. Let me put it on the bed of nails, add some force. Nothing. We go down, less dense, more pressure per area. Still nothing. Now we go to the very last one, less dense, even more pressure per area, and just like that. But I'm a physicist, and I believe in my science and in this relationship between force and area. So what I'm gonna do is take this right here, and let's wheel that out. We have a bed of nail right here, highly dense, very heavy, and I'm gonna put it on the floor and take a nice little seat. Nothing's going on, I'm perfectly A-okay, and it's actually pretty comfortable. Just like, you know, a little bit of acupuncture, but all good. Thank you guys for coming, and enjoy the rest of the festival.
Here I have a stack of washers. What do you think will happen if I hit one of them with my kitchen knife, like this? I will destroy the whole tower. Let's check. Ready? 3, 2, 1. It stays! It stays! Because I hit it fast enough. Other washers, they have inertia. They didn't have time to move. Let's do it again. Nice tower. Ready? Let's go! Yes, we did it! Done. It stayed. Do it at home and be careful with the kitchen knife.
Okay. Chaos. My favorite term in physics. Slightly incorrect, but still pretty cool. Chaos is basically everywhere. It is in this building and also in this very room. Here I have something called a double pendulum. These things are very dynamic and also very chaotic. It makes it really hard to predict what's going to do. Here I have 2 degrees of freedom, one here, which makes it, again, hard to predict its motions. If I bring this up, all the way up here, highly dependent on its initial conditions, certain results will happen. But again, I can't predict that, and neither can anybody in this room, sadly. Unless we have some really strong mental people here. I'm gonna let it go, let's see what happens. 3, 2, 1. Let me stand away from it so I don't get hurt. Oh, it's like a butterfly knife. Super cool, but let me stop it. Okay. Got it. As I said before, it is highly dependent on its initial condition. So I'm going to show you what I mean by that. I'm going to bring up a second one from the back. I'm going to try my best to start it at the same height with the same conditions, but they will differ ever so slightly. So the effect and the result will become apparent after a couple of seconds. 3, 2, 1. As you can see, they're already highly different from each other. This is due to chaos theory. But these are not really my particular favorites. because if I can stop it, oh my God, please stop. I have one over here that I find to be more mesmerizing. It is called the bar and ring pendulum. Now watch what's gonna happen. I'm gonna do the same thing, raise it up, give it some extra energy, and look at that. Beautiful, mesmerizing. It's almost like almost like a basketball at some point. There we go, just like that. I'm just dribbling the ball right now. Beautiful. All right, these are our chaos pendulums here at the physics department in Texas A&M University. Hope you guys enjoy the rest of the festival. Gig'em. Okay, please stop. Thank you.
Have you ever wanted to play music but don't have a wire long enough to get yourself to the next outlet? Well, I have a solution for you. So what I have here is a speaker, and this speaker is connected to this amplifier. But this amplifier is not connected at all to my phone. My phone is connected to a second amplifier, which is connected to this coil. So when I go ahead and start playing a song, which many of you should be familiar with, a current will pass through the amplifier and pass through this coil. That current will generate a magnetic field, and a changing magnetic, and that magnetic field will pass through the second coil. And Lenz's law states that nature hates a changing magnetic flux. So a current is induced in this second coil, which passes through the amplifier and to the speaker. And to prove to you that it's actually the magnetic field that is causing this sound, I can start by removing this iron core. And when I remove the iron core, I weaken the magnetic field that's inside these coils. Furthermore, though, if I turn one of the coils, the sound completely goes away. So this is a demonstration of Faraday's law, Lenz's law, and mutual inductance. I hope you enjoy the festival.
I have two heavy bowling balls here. Now, what do you think will happen if I start blowing air between them? Well, they will move apart, right? Let's check. Let's do it. Did you see that? They actually come close. Why? Bernoulli's principle. The higher the speed of airflow, the lower the pressure in it. Then there is force from high pressure to low pressure that brings these balls closer to each other. Now, I have one more experiment for you on Bernoulli's principle. I will use the Bernoulli's principle again. Thank you, Nicole. Can you put this ball in the airflow? We will put this ball in the airflow, and the airflow will push it up. Okay, let's do it. Why did it stay? I tilted it and it still stayed there. It was stable. Why? Bernoulli's principle. We created high speed of air around the air ball, low pressure. And then there is force from high pressure to low pressure that kept the ball in the airflow. It kept it stable. Try this at home. It's a challenge. Try to land this ball with leaf blower in the bucket using Bernoulli's principle.
This is our LIGO demonstration. What we have here is what we call an interferometer. And an interferometer is all about a laser which passes through a beam splitter, which then sends light in two different directions, which get reflected, pass back through the beam splitter, and then combine to create what we call fringes. Now, LIGO are two separate interferometers. One is in Washington, the other one is in Louisiana. These interferometers are so sensitive that they can detect local phenomena such as trucks going down the highway nearby. Why do we need two interferometers? To detect gravitational waves. Gravitational waves essentially can affect space-time, ripples of space-time, and can move matter fractions of an inch, even smaller than that. So what I'm going to do for you right now is I'm going to show you a demonstration that kind of displays this phenomena. So I can't create a gravitational wave, but what I can do is shout, "Howdy! Gig 'em!" So hopefully you saw that this fringe shifted. These little dark lines and bright lines were able to move just by me shouting at the mirror. When I shout at the mirror, an incoming pressure wave causes the mirror to move back just slightly. Light is so sensitive that it can see this shift and cause an interference effect because light is a wave. I hope you enjoyed this demonstration. Gig 'em!
Hello everyone. Here I have a demonstration called the L-into resistor. So first off, let me actually get ready. Have my goggles on, have my gloves on. Last thing I need is some good old liquid nitrogen. I'll be on radio at that point. Just like so. Cool. Awesome. So now what I have here is a complete circuit with some power supply right here, a light bulb next to it, and then a resistor at the very, very end, just like so. What I'm going to do is run a current thanks to the power supply through the circuit, and what will happen is the light bulb will be really, really dim. But once I put the resistor in liquid nitrogen, I will reduce its resistivity, increase its conductivity, and have more current go through the circuit, making the light bulb shoot up in brightness. Let's give that an attempt. We turn this on, put it right there, and we see basically nothing. But if I take this right here and stick it in just like so, eventually, hopefully, it will start lighting up just like that. It's a cool demonstration. I love this one. And no pun intended, I hope I'll probably be cool. Thank you everyone and enjoy the rest of the festival.
This demonstration is on pressure. Each of these light bulbs is very fragile. I can easily break them if I step on it. However, if I have 3 of them and I distribute my weight among 3 of them, we'll see a very interesting effect. Let's do it. I put them on the floor. And now I'll step on it. 3, 2, 1, I'm doing that. I trust in the laws of physics. Yes, it works. We are safe. Please don't do it at home.
Howdy. Today I have a demonstration for you on index of refraction. So you notice that on the left side of this aquarium that we have these colored beads that are filling the water. But the other side looks completely empty. But if I put my hand inside, you notice that there are all of these very clear beads that are actually filling the tank. Now, these beads absorb water very, very highly. So their index of refraction nearly matches that of water. These are the same type of beads, but they're just colored. So light can't travel through them the same way that it travels through these clear beads. When the index of refraction of 2 materials is basically the same thing, light can pass through it seemingly unobstructed, and then the beads become invisible. I hope you enjoy the festival. Gig 'em.
Wow, weren't those science demos cool? We can see you've all been asking some great questions, so let's get right into our Q&A.
Hi everyone. So there was a question on the chat. How do mirages work? It's a great question. It turns out that air can work also as a lens and refract light, and in particular when it's very hot. Then the layer of air just above the Earth's surface works as a lens which curves light rays, and they can go around the horizon. So you can see something which is actually beyond the horizon, which you would not see otherwise, because the light rays scattered from they just curve around and come right into your eyes. So it's a great question.
Why do people typically associate mirages with like the desert or something very hot?
Well, that is why, because that's exactly where the air is hot and dry, and that's exactly where it makes this kind of lens-like layer just above the ground, or the sand in this case. But you can also observe the mirage when, for example, you drive and it's a very hot day, and then just the road becomes very hot, and then you start seeing like a reflection of the car from underneath. Obviously, there is nothing under the road, but that's how it looks like.
Yeah, we get that a lot in Texas. Thank you.
Exactly. Thanks.
And for our next expert, we once again have Dr. Welch.
So somebody seems to have a question, how do fiber optics work? And what an incredibly important question, because fiber optics are responsible for our modern life. I mean, there are tens of terabytes of data transmitted every second in the United States alone. And it didn't used to be that way even 20 years ago. We didn't have that kind of society. You can't do that with copper wires. You have to use optical fibers to send data that fast, because the frequency of light waves is very fast, so you can do it. But how do fibers work? Why is it that you can send light down a little glass fiber for hundreds of miles without it leaking out of the fiber? And I'll give you an analogy. Some of you may have been in a swimming pool. Anybody ever get in a swimming pool? Maybe it helps wearing goggles. And get down below the surface. Hold your breath. Go down below and look up. And if you look straight up, you can see right out. You can see somebody standing at the edge of the pool. But if you look off at an angle, all of a sudden the top of the water turns into a mirror. And that's called total internal reflection. It's because light changes direction when it changes speed. And the speed of light is slower in water than it is in air. So if you're outside of the pool looking in, you see some light bend when it goes in. And the same thing happens if you're in the pool. You see the light would bend the opposite direction when it comes out. Now, if you go to a big enough angle, then the light would bend more and more. And once it hits 90 degrees, it can't bend anymore. So light simply can't get out of the water at an angle bigger than that. It reflects and the surface becomes a mirror. And that's how the optical fibers work. They're thick. The speed of light in that glass is a lot lower than it is outside, so the light can't get out. I mean, if it came out at a big angle, it could, but as long as you keep the angle relatively small, then the reflection is perfect. It's the only place in nature where we have an absolutely perfect mirror. And by perfect, I mean literally, theoretically 100%, not just something close. Now, you may be thinking, well, if you've spoken with engineers, you know that light eventually does stop going down the optical fibers. They can't go forever, and there are repeating stations. And that's because it's not possible to make glass that's perfect with no impurities. So there actually are some impurities, maybe a little bubble, and when the light hits it, it scatters, and so then the angle can become big, and if it becomes big, then it can leak out. So our optical fibers don't transmit light, an infinite distance, but it can go a long way. And certainly between cities is no problem. So we can send vast amounts of data now. And I just looked up, I believe right now in the United States, it's about 10 terabytes per second, which is just a huge amount if you think about it, of data that's being transferred. And when I was young, people sent, messages on the telephone. It's very, very different now because of optical fibers. They've really changed the world.
Wow, that's really cool. Thank you so much for that. And for our next expert, we once again have Dr. Belyanin.
Hi everyone, there was a question on TikTok, how long has the Earth been around? It's actually not so easy to answer because the surface of the Earth has been damaged or modified by erosion from its, primordial primary surface, but still finding some places that were relatively intact, or looking at, deep in the mines, or looking at some deep canyons, we still can find layers which are very old, and then we can date them using radioactive dating, observing some long-lived isotopes like lead isotopes that decay but over a very long time of billions of years, and then the answer will be about 4.6 billion years. And we can get even a better answer if you look at the meteorites, at the lunar rocks, for example, or meteorites which are hitting the Earth, because it's generally accepted that the solar system and all the major planets, they were formed more or less at the same time. And then when you see all these pristine, unmodified meteorites coming from space, we can also date them. And it all points out to an age of about 4.6 billion years.
Wow, that's a long time.
Thanks.
Thank you so much. For our next expert, we once again have Ryan Mueller. Welcome back.
Thanks. It was a great question in chat. How will the universe end? And it's a kind of complicated question because it depends on some cosmology that maybe isn't completely understood, but is being actively studied. It kind of depends on what happens with expansion. So the universe is expanding, and actually expansion is accelerating, which is kind of a bizarre thing. That's actually where we get dark energy from. Just as a callback, people said dark matter makes up some huge chunk of the universe. Dark energy makes up a huger chunk of the universe if we just look at it in terms of energy. So how does this relate to everything? Well, if the universe is expanding and it's accelerating, then as the universe gets older, you can actually end up in a scenario where things just get further and further away. And as entropy progresses and everything starts evening out, you just end up with a universe that is, in some sense, kind of boring, where it's just everything is spread out in simple matter. And this is referred to as the heat death of the universe. Alternatively, if expansion is particularly aggressive, you can have like a scenario where things actually get torn apart. Or alternatively, if expansion doesn't continue, and you can even have a situation where things fall back together and you end up with things becoming closer and closer together. But it really depends on how expansion and the rest of the universe plays out.
Wow. Never really thought about that.
Looking back in the chat, I saw some discussion about negative temperature, and it actually kind of followed the question I talked about earlier about can something reach absolute zero, and there was a little bit of discussion about that after it in the chat. And negative temperature is something I don't want people to be very confused about. So everybody knows water freezes at 0 degrees centigrade. So that's where we call zero. And temperatures that are below the freezing point of water, we say it's negative. We just make the temperature be a continuous scale. But as you get lower and lower and the molecular motion slows, the point where molecular motion has reached the value that's as low as it can go is called absolute zero. And that's 273 degrees below 0 centigrade. The freezing point of water is 273 degrees above absolute zero. So if you measure zero from absolute zero, then negative doesn't sound like it makes any sense. And in fact, if temperature maintains its sort of well-defined meaning as an average of macroscopic things, then yes, negative temperature doesn't make sense. But as I mentioned earlier, you can specialize. You can talk about a subsystem or a small part where you don't have as many atoms as there are altogether. And in a separate system, then actually negative absolute temperature makes sense. But it makes sense in a funny sort of way, because for the isolated system, as you keep adding energy, temperature goes up. But the way we define temperature, things get strange. And it can actually be that when the temperature reaches infinity, that you haven't added all the energy that you can. So if you add more energy than that, what do? You've already reached infinite temperature. So what we do is we say a little bit higher than infinite is minus infinity. And then as we add more energy, the temperature comes up from minus infinity. So as negative temperatures are actually, negative absolute temperatures are actually much hotter than positive temperatures. So it's a very strange way of looking at things. And in fact, it's not clear to me how important it is. It's only in very specialized cases where people are not looking at an entire system. They're only looking at a piece of it, that this negative absolute temperature could make sense. So I hope that answers the question about that, or maybe it makes it more confusing. I don't know. Yeah.
Maybe a little bit more confusing. Who would have thought that a negative temperature would be hot, not cold?
Yeah, well, I mean, and in fact, for real things, where you're looking at an entire system, that doesn't happen, of course. Absolute zero is as low as you can go.
That makes sense. Thank you so much. And for our next expert, we have a newcomer, Dawson. Dr. Dawson.
Yes, Dawson's fine. So I saw a question in chat about light years. I just wanted to about how fast you could go if you were traveling light years. So light years is a measure of distance, not a measure of speed. So when you take the speed of light and you multiply it by essentially a year of worth of time, that tells you how long, how far light has traveled in a single year. So it's a misconception to think of light years as a speed rather than just distance. So that's really the only question I had, or that I saw the answer. So hope everyone's enjoying the festival. We're having a great time over here, giving you all this fun demonstrations and information. So
I know I am. I love those demos. All right. And with that, we'll close the second Q&A session. Thank you everybody for participating in this Q&A. And once again, we would like to thank Halliburton, Ralph and Marsha Schilling, class of 68, Nancy and Robert Dunham, class of 63, Intellite Technology, Colonel Hal Shade, class of 67, and Ramiro Galindo, class of 60, for making this year's festival happen. Just a reminder that you can enter for a chance to win a bundle of science goodies like a t-shirt, skyhook, diffraction glasses, and more delivered to your door. Just go to tx.ag/science giveaway. There's a link for that in the video description as well. Finally, be sure not to miss interacting with physicists and more demos live at 12 p.m. Central Time. A link for that will also be presented on the screen later. Now, let's get ready for our first speaker, Dr. Nancy Curie-Gregg, with her Dr. James G. Potter lecture, Out of This World Repairs, Servicing the Hubble Space Telescope. See you back here in a few minutes as we take a quick break.
Okay, good morning, everyone. It is such a pleasure to see you here, and it's been a while. So now we are again back with Physics Festival in person, and my name is Grigory Rogachev. I'm head of the Department of Physics and Astronomy, and it is my distinct pleasure. You can't even imagine how what I feel toward the speaker who is going to present today. This is our speaker is Professor Dr. Nancy Carey Gregg, and she is, well, yes, she is NASA astronaut, but she is also a military pilot, and she participated in 4 shuttle missions. She contributed to the safety of the NASA space missions dramatically because she led the committee, I think it was called the Committee or Commission for Safety and Mission Assurance. So she contributed to our nation so much, to our universities so much, and also to our department. So it is a distinct pleasure to introduce our speaker, but before I let her speak, there is another thing that I want to point out. This lecture is a special one. It is an inaugural lecture because the festival was recently endowed. We received a huge gift from a person who is sitting right there, Bob Dunham. Is right there. So thank you very much, Bob. And he asked us that we name this lecture after previous, well-known, great department head of this department, James Potter, who actually made a huge difference in Bob Dunham's live. So thank you very much, Bob Dunham. And now this is the inaugural James Potter Physics Festival Endowment Lecture. And now, Nancy, please, the floor is yours.
Howdy! Howdy! This is awesome. If you don't know, all Aggies greet each other with howdy. All lectures at this university, I think, across the board start with howdy. It is fantastic to see people back in person in the Physics Festival. I've spoken the last 2 years online, and so it is so great to see people not only online, because I know we're streaming this as well for people who cannot attend, but to have people in the room. This is meant to be, just like I teach, very interactive today. So I'm going to leave some time for questions at the end. Do a little bit of Q&A. We'll have an interactive session. You can ask me anything you want. You can ask me anything you want. So what I'd like to do today is to talk about one of my 4 space flights. Turns out it was my last mission. I really didn't know it was going to be my last mission, but we'll talk about why that was. Because this was the last time that the Space Shuttle Columbia successfully launched and landed after a mission. We were STS-109. You know anything about the Space Shuttle program, you might know that we had an accident in early 2003, the year after this mission, on Space Shuttle Columbia. Mission successfully launched, did a 14-day biomedical research mission, but unfortunately on landing, because of some damage that occurred at the time of launch, the spacecraft broke apart approximately over Dallas, Texas at 200,000 feet. Then I took a pretty hard turn in my career. They told us if you've flown 4 times, your flying career is over. We had about 70 astronauts. We had about 130 astronauts total in the office at the time, and 70 had never flown in flight in space. And we were gearing up for not only completing the construction of the International Space Station, but also for future missions, like a mission back to the moon, a mission on to Mars. We thought it was really imperative when the Accident Investigation Board said that the shuttle should eventually be retired, that we get people experience flying in space. So for the next 15 years at NASA, I stayed there for 30 years until I came here in 2017, I supported spacefaring astronauts in safety and mission assurance and then engineering at the Johnson Space Center. So this was our crew. We launched on March 1st, 2002, so I just celebrated the 20th anniversary of this flight. What do you think about when you see that crew photo? I know what you're thinking. Okay? And the answer might surprise you. Yes, I was tall enough to be an astronaut. And no kidding, I'm no longer tall enough to be an astronaut. This year they just increased the stature requirement to 62 inches. So I think I hold the world's record of world's shortest astronaut. You can Google it. Everybody's got to be famous for something, and apparently that's my fame. And I get to hold that title apparently for some unspecified period of time. But you can see it was 6 male astronauts and myself, and we embarked on a 12-day mission to go service the Hubble Space Telescope. Now it's interesting because all of my previous flight assignments were secret. I didn't know I was going to be assigned to the flight until they announced the crew. My fourth flight, a friend of mine, an astronaut classmate colleague of mine, was the chief astronaut. He called me down and he said, we have 2 missions that we need a flight engineer and a really good robotic arm operator. And on all my flights, I was a flight engineer and robotic arm operator. I said, well, that sounds really good. And he said, one is to service Hubble, one is to return to the International Space Station and continue the construction. And on my 3rd flight, we took up the first space station. We made it to the first Russian segment, which was launched on an unmanned rocket 2 weeks prior to us. We rendezvoused 215 miles up in space, flying Mach 25, 17,500 miles an hour. Basically, flew formation. I reached out with the shuttle arm and grabbed it. Everybody had a huge sigh of relief. And even a bigger sigh of relief when we mated that to the first U.S. segment. We did a series of 3 spacewalks, went inside, and we made that very first call, Houston, this is the International Space Station. Professional career, that probably ranks way up near the top, right? I think I was the 4th person in because I had the camcorder, I was filming everything. The first 2, side by side, a Russian cosmonaut, U.S. astronaut, side by side, went through the patch together, symbolizing partnership of our nations coming together to build this incredible laboratory up in space, 215 miles south. That was a really tough call. Do I service Hubble? Do I go back to the space station? Ultimately, I didn't make that decision. I called another friend of mine. I said, who else are you thinking of? And they told me, another classmate of mine. So I called her down. She ultimately became the director of the Johnson Space Center just a few years ago. I said, Ellen, you're not going to believe this. We get to pick our next flight. And I told her what the 2 flights are, and she said, wow, that's a difficult decision. How about if I go talk to my family, I'll come back tomorrow and tell you which one I picked. So she did that, and she came into my office the next morning, and she said, I really think I want to go back to the space station. So I said, okay, well, I'll take the Hubble servicing mission. She left, and I was doing a happy dance in my office because Hubble, if you don't know, was not always a success story at NASA. But we turned a failure into an incredible success. And to be a part of that was absolutely fantastic. So I'm going to talk to you today about that voyage. First of all, a major objective on our mission was to go change out the solar arrays. These are pretty big solar arrays, about 25 feet long, about 8.5 feet wide. And these are semi-rigid arrays. They're like books, so we open it almost like a page of a book. The previous arrays were almost like a blind that you roll up. Now, We changed out the solar rays one previous occasion on Hubble, and when we did that and the crew went to roll up the solar rays, one did not stow because there was some degradation from the time it had been on orbit, and so they had to throw it overboard. And when they threw it overboard, it looked like a bird flapping away. So we had an onboard wagering of, hey, are ours going to stow or not? But you'll see in the movie I'm about to show, everything went fine. And then we installed these new solar panels, and you're going to see the difficulty. That was not an easy task. You might be wondering, how do we train for a mission like this? So we did 5 consecutive days of spacewalks with 2 groups of spacewalking astronauts. NASA vehicular, we call that the extravehicular activity. Okay? And our suit that we wear is the extravehicular mobility unit, or EMU. That's what we call it EVA, extravehicular activity, because you're outside the spacecraft. And the way in which we train for that is in a huge water tank called the Neutral Buoyancy Laboratory. That suit is filled with air. If you were to take somebody in a suit, put them in the water, they float. So we actually weight them down so that they're neutrally buoyant. They don't rise, they don't sink in the water. And then we can do tasks like free float. So question I always get, what does it feel like to be in space? I always tell people, go into a swimming pool, totally relax, put your head in the water, act like you're asleep and float around. That's about as close as you're going to get. Now the difference is the viscosity of the water. So as you're moving around these big solar rays, the viscosity of the water, it's actually more difficult in the water tank. Sometimes we have scuba divers to help us move things around. The spacecraft itself, right, is pretty big. It was about 24,000 pounds when it launched. After 5 service missions, it now weighs about 27,000 pounds. As we've upgraded it over time, it's about 45 feet long. And trust me, I saw it close up as we redeployed it into space. I'll talk about our reaction to having a 45,000 pound spacecraft come right over our head a few feet above the windows. That was interesting. And obviously the mirror is a critical facet of the telescope. Believe it or not, the pointing accuracy of this is equivalent. I'll give you some equivalency. At a mile, it can basically see the diameter of the human hair. So incredible pointing accuracy in this telescope. Obviously, the mirror is an incredible engineering. So we launched on March 1st. We were considered a night launch. We actually launched right around 6 a.m. As you're preparing for a space shuttle mission, any space mission, you go into medical quarantine a week before the flight. Why are we going to quarantine before the flight? Well, before COVID, we thought about the crew getting sick and being exposed to germs before they flew. Anybody know the story of Apollo 13? Right? The crew member that was exposed to the germ measles had to be pulled off the mission. So we go into medical quarantine a week before the flight, mostly to keep us healthy, so that we're not exposed to any illnesses. Because every single minute of the mission is planned out, right? And especially the spacewalks, the EVAs. We have consumables for roughly about 6 to 6.5 hours. Of course, you don't want anybody to run out of oxygen or lithium hydroxide, which scrubs out CO2. So we put a little buffer of about an hour and a half. So we say, you know, roughly we could make it for 8 hours, but we don't want to really plan for anything longer than 6.5. But in one of our really critical EVAs where we turned off all the power to Hubble and we changed out the power control unit, nominal plan was about 7 hours. So we had to be at peak proficiency and our peak aptitude. So being in good shape was really fundamental to the mission. All right, so now what I'm going to do is to show you a movie, because I want to take you inside the spacecraft and a little bit outside to show you what is it really like to fly in space, and I'm going to narrate through this. countdown, all NASA movies have to have countdown. Now, we trained for about 2 years for this mission. So your job for 2 years is waking
You
up
know,
every
we were
day,
assigned about a
getting
year
in the
before
simulator,
flight,
staying
but
in the
before you knew it, it seemed like we were
This is
sitting
on the
in
morning
the
of
white
launch.
room
This
putting
is
our
our launch
suits
and
on.
entry suit.
Here we all are on
told,
launch
with the
day about
parachute,
4
this
hours
equipment
prior.
weighs about 82 pounds.
This is
I weigh about
Nancy Curry, our
98 pounds,
MS2. It was her fourth
right?
flight.
And so, you know,
ready to go,
this is
and
not
Jim.
easy. But I had to remind myself that at the
And
age
Mike,
of
uh,
78, John
he's a New
Glenn
Yorker, you
in
can
the
tell.
Space and Shuttle, right? So
Then on
we know where
walkout,
we're
it's
going.
kind of like coming downstairs on Christmas
Walking
morning. It's just an
down that
unbelievable
same
thrill
ramp, out of
as you
that
get
same
out there.
facility where Neil
Of course, the vehicle's
Armstrong,
parked
my
in the
personal
vertical, so it's
hero,
not like
walked
jumping into
on.
your car. It's a little bit of a
Really
haul
kind
to
of
get
puts
yourself
mission
into
in
the seat.
perspective.
And
This
some
is
of us are a
Scott
little bit
getting into
bigger
the
and have a
seat,
little bit
you
more
know.
trouble.
He's that big guy you saw
You
on
see
the
Mike
photo.
getting
He's the
himself in there,
commander.
all the suit tech
And
helps.
so the vehicle is in the vertical. So you
30 minutes in, 9, 8, 7, 6, main engine start,
see you getting in your seat wearing 82 pounds of equipment.
start on space shuttle.
Those big hold-down bolts,
Computers,
right,
space
they're
shuttle.
meant to be frangible bolts to release at the point at which the solid rocket boosters are lit. The solid rocket boosters each provide 3.1 million pounds of thrust, and the 3 space shuttle main engines provide about 375,000 pounds of horsepower. And so that's about 7 million pounds of thrust to get that roughly weight of about 4 million pounds off the launch pad and off into space. We only ride the solid rocket boosters for about 2 minutes and 20 seconds, and at that point, you can actually see from the interior, an explosive charge comes off, and they actually come back, they would flow back under parachutes to the water, would be retrieved, and then go back in and refurbished.
Spoken.
This
8.5
is the
minutes later, we were in.
tank that holds the fuel from the main engines, and that actually, as it descended back to the atmospheric heating, would cause that tank to
We reviewed up
explode
from low,
and little
up till it's
pieces,
just hanging there,
very,
just
very,
above
very
the
small pieces
bay.
come down.
This
That's
is
an
a shot of the
animation
flight
of
deck
how
very
we were
roundabout.
going to
You see
approach
it
Hubble.
working very clean.
Hubble
Rick Linehan was
was
our
the
handheld
highest
operator. That's
mission
why he
that
was
the
our
shuttle
range
ever
to
flew,
the telescope and we slow down to
350
see it.
statute miles above the Earth.
It really
And
was
this is what it
beautiful
looked
sight
like
to
as
see
we
it,
approached
out
it
there.
again,
Of course, flying the
about
Bug
the
is
size of a large bus,
Tim
weighing
Hughes,
about
our instructor, taught
45,000
us everything.
pounds.
He was there with us there as we
And at that point,
pulled up to the
you're
telescope. You
flying
can sit through the optical
formation.
sight there.
So you're flying formation by
Nancy
firing
used
the
the
jets
robotic
on
to
the
reach
shuttle,
out and
and then this
share
is me
Double
operating
space
the robotic
telescope
arm. We
on
have
the aft
2
deck
hand
of
controllers, a
This is the view that
translational
you
hand
had. She
controller,
was pulling
forward,
out
aft, up, down,
over
left,
from the
right.
snares.
The
And you can bet
rotation
that
hand-
once we hit
rotational
the
hand
board,
controller
there was a
is
lot
the
of have
end,
was a
what
big
we call
sense
the
of
end
you for those
effector,
engines.
which is used to grapple that target fixture.
Of course,
When
once
we
we
go
hit the
down
Hubble,
over the
we
grapple,
had an
we
ambitious
close the
something
snares,
of rolling
and
up
then
the
we
solar arrays.
rigidize
Our
that
first service in
spacecraft to the
1961
arm.
that Jet 1 array, so we were very
And
anxious.
so the old solar
to see
arrays
this kind of
rolling
pivotal
up.
rotate
We
telescope
were
here. One
really,
rolled
really
stone.
pleased that they both
The
rolled
one
up.
off we had was
Otherwise,
second,
we
and we
trained
rolled
for
up the second
contingency
one.
where we
We were
would
very
literally
fortunate both
throw
solar
them
arrays are
overboard
up.
because we couldn't bring them
That set
home.
the stage today, first of 5
rolled up.
SWATs
We brought them
activities.
home and they were
We find
analyzed by
the
the
solar array
European
days because
Space
over the first 3
Agency,
days, we replaced
looking at
nearly
the
the entire system of
degradation
Hubble.
of solar
We started out
arrays
by
over an
stowing
extended
old solar
time
arrays, the solar array
up
chips,
in
these are
space,
raised by the
because you
European
have,
Space Agency.
atomic
One of the partners on the Hubble
oxygen,
Space
you have
Telescope,
small
and so it
micrometeorite orbital
station.
debris.
This is a
that
view
can
from one of the
ultimately
helmet cams that was
degrade
very
that.
useful throughout the
And
mission.
then it was
And
time
you'll
to
have
put
today
in
to see some of the
the
views
new solar
inside a
arrays.
spacesuit.
So we
After
did
removing those solar arrays from the
2
telescope,
full
we brought them
spacewalks
back
to
down
put
into the
one
mud
each
bay
of
and
the
stow them on
solar
the
arrays
carriers that
in.
we brought
The
over
first
to
thing we
the
had to do
pit
is
bay.
take the old ones
And
off,
using the
stow them
controls
down.
on the lower
This
right,
is stowing
lock
them
those down
into
the
a
bay for
protective
burn
carrier in the payload bay so that we can bring them
periodically,
back
Ivy crew
so the
members
scientists
were integral to
scientists
the
can
apparatus
analyze those.
and run
And then
themselves
we had to
to
take out the new rigid, semi-rigid arrays. Now the interesting thing is, these things were big enough and massive enough that we could not tether to them. Anytime you're out in a spacewalk, you tether to all the tools. So if I'm not tethered to this pointer and I drop it in space, it becomes an orbiting object, also traveling at Mach 25. You don't want to see that on the next orbit, right? Because if it hit us, traveling at that speed,
and got
it
mass
causes
of the new solar
catastrophic
array for the
damage to
telescope,
spacecraft.
it was time to
So we
insert it
usually
into the
tether
telescope.
to
You can see
everything.
the
clamp
These
and
things were
pedals
so
and,
massive,
solid
it was
going into
deemed
the
to be
clamp and
unsafe if we tethered to them.
pulling it down.
We basically told the EVA
There were a lot of
astronauts,
lights on while we were doing this.
don't let go.
The new solar is unlike the old one, folded like
And to make
the
things
old
even
machine
more
or the old head.
complicated, from the position they were in when they extracted them from the payload bay, and they're in the end effector, they're in the end of the arm on a foot restraint the whole time to help them move around, right? Otherwise, they would have to use one hand to move them around and one hand to control this massive solar array. So the best thing to do to do a spacewalk is to move them around on the robotic arm. Gives a lot of transition time, also helps them to concentrate on stabilizing the object that they're crafting. Now this is a reaction wheel assembly, so why did we jump in line in front of STS-107, the Biomedical Sourcing Mission, also flying on Columbia? It's a reaction wheel assemblies that started to degrade, and they are used to point the spacecraft. Can't point a telescope, can't do science, so we were
EV3 we
deemed
went
to
out
be
for, we thought it was going to be the start of EV3 and the control unit change.
Every mission has
the collision
something
of
that
power
doesn't
supply,
go according to
water
plan.
supply, and one of the
This
suits
is
leaking.
one of our
So we had
suits
about a 2 hour
developed
delay
a
when we
leak
resized the suits. They were
on
designed to do
the
that in orbit.
same
And
morning
features
of
the
that really
network
long
spares.
planned
So I went out
7-hour
with Jim's
go
backpack
change
and
out
we
the
set
power
out to
control
the
unit
telescope frame it
spacewalk.
here. That was a
And it
battery.
basically dumped
This
a
is the
couple
power
of
control unit.
gallons of water
I think all of those connectors on the left
into
side, they
our-
were connected for
our
themselves.
mid-deck,
But it
the
was a
lower
day to
part
manage
port
frustration
of the,
and carried on one
space
connector at a
shuttle.
time.
And
Disconnected
so,
all.
we had to
from
go
the
get
left
all the towels
swap
that we
the
had on
box
board
in,
and
this is the
then
front
reconfigure a
in with
spare
me,
suit,
outfield,
take the arms off, you
and the
know,
reverse,
take the gloves
one by
off
one,
and
one connector after
reconfigure, get
another,
him back in
and all
that
those
suit and get him
connectors
ready to
back
go.
on. Special tool to
This
help
is
us
the
do
power
that.
control unit.
36 connectors later.
Actually, the
PCU
mission
is
before
complete.
us, the service
One
Hubble,
picture
had
of the
said they
pulse
would
line
not
UV3,
do
and we were ready to
this
set the stage
part
for
of
the
the
next
mission because they didn't think it would be successful. The power control unit had been there since the time of launch, had been exposed to very, very cold environments, you know, minus 250 degrees, all the way to plus 250 degrees, and they were afraid that one of those 32 connectors or more might not come on. If one of the connectors didn't come on, you couldn't change out the power control unit. Oh, by the way, all 32 didn't go back on. We were the crew that killed Hubble. Nobody wants to be the crew that killed Hubble, right? Luckily, all that training over a few years, specialized tools, because you can't fit, you can see those gloved hands, it's pretty hard to do, to get in there and make a connection with an electrical connector, right, and rotate that collar, so we develop specialized tools to do that. Now these guys actually got to go inside the spacecraft. So one ground rule is you can't take your boots inside, so we have to be very cautious about that. And again, the crew member that kind of went inside the telescope was on the end of the arm, so it was on the end of the arm hanging in there. But we did that because we put in a new instrument called the Advanced Camera Survey.
Now, Jim, after he hands off, will be free floating,
The really
making
cool
his
part
way
about
up
this
the front
mission
telescope.
was
Mike
probably
flies
a
up.
week
You
after
can
the
see
mission,
picture of
getting
his
the
home camera right
first
there.
images from
They've
that
got that
camera,
installed, and
which
they're
were
beginning to
phenomenal,
replace the
one of the
connectors
best
on the
resolution
man
cameras
connectors
they
that
had
go
on board
in,
the
and
telescope,
latch on your hand.
and to see
Nice
kind
to
of the
reminder,
results
as he
of
free
our
floats, zooms
work.
across, you can see the headlights and the camera,
This is
as well as
Jim
Jim gives us
Newman,
the
who I
afternotes,
flew down on my
Chris
third
taking his
mission
pics.
with, but my
And
fourth
really nice
mission,
true Jim.
that was
Pete,
his
he's on his
final
back there waving
spacewalk.
goodbye to
I
Earth.
think he
That's
kind of knew it was
the
probably going to
really
be his
pretty
final spacewalk.
Now, we're going to be electricians and plumbers on
waving
EVA
goodbye
5.
to space,
We're bringing a new
from
cooling
the
system, an
outside.
upgrade unit to
So
replace
we
one
put that
of
instrument in, and then we had to button up
you can see
the
the robot on there.
telescope
We're
doors,
getting the
right?
NCC large black box
You
with
can
the
see
ESM.
that
John Glow's in the
this
coverage
one
of the
was
special.
actually a large
on
array.
here is on the end of the arm, large radiator arm. It's actually go on the outside of Hubble. It's changing the way Hubble looks, and that we're hanging a huge radiator on the back. And you'll see in this skid, we've got a large conduit full of plumbing and electrical cables. We'll actually route un-Hubble and bring it back up inside the bottom. And that which saw there is what's being pushed up me. You can see me down there on the bottom.
This
We
near
installed the
infrared camera,
conduit.
the
John's
cooling
going
system
through,
had been
and eventually we'll
expanded.
hook that up
So
top,
somebody came up
peel
with
open,
this
take
really
these
great
cables,
idea
and
to
everything
put
runs up.
this big radiator on the exterior, literally hang it on the outside of the spacecraft. So that's what we did. We hung this big radiator on the end of the spacecraft and then threaded the conduit up back into the spacecraft to provide cooling to the. You can see the Earth going by in the background. People say, is that kind of disconcerting when you're on a spacewalk? Never been outside on a spacewalk. It wasn't a suit that fit me. But most crew members say that for the first few minutes when you're outside, even though you know you won't fall in space, when you look down and see the Earth 350 miles underneath you, you know, you hold on just a little bit tighter, even though you're smart enough to know that you're not going to fall. This was redeploying Hubble back to space, and it was done again with a robotic arm. That was my job. We maneuvered it into position, and then I backed away with the arm, and then we fired jets on the shuttle. And the orbital dynamics took this thing right over the crew compartment, literally feet above our head, over the overhead window. And we did something in space we never did in the simulator. We all ducked. Right? So 7 trained astronauts all ducked. And then it was immediately the other thing. I was still trying to fly the arm. I was overrun with 5 people with cameras and video cameras taking images like that. And that also never happened in the simulator. So I was kind of down almost on the floor, still trying to move the arm out of the way. This is a little bit about living in space. We got to live there, right? We're there for almost 2 weeks. This is a psycho-ergometer. So every day we would bring it down to the mid-deck because it's very important to stay in good cardiovascular condition, muscle condition, bone density decreases in space, muscular adaptiveness decreases in space. And then the ultimate is viewing the world from space. I will tell you as an astronaut, it is not flying in space that changes you. What changes you is seeing the Earth from space. For the very first time in your entire life, you see this universal perspective of the world. This is us redeploying, and you can see we're firing the jets, and I had to hold on. It was like Superman, right? Because we're accelerating the spacecraft, and I immediately started to fly to the back. And then this is on entry. So as you re-enter the Earth's atmosphere, from the time you burn the deorbit burn, and you only decrease your speed by 1%, that starts you on your trajectory back home. And as you re-enter the atmosphere, you see that atmosphere heating. The forward windows turn, kind of pink and then yellow, brilliant orange. You know you're flying in a fireball. You know you're flying in a fireball. And then we came in. We also landed very early in the morning, essentially at night. This is an infrared camera, so you see we waited until 300 feet above the ground to deploy the wheels. And the reason why we did that is because this is a 200,000-pound glider. And as soon as we deploy those wheels, right, that's going to slow our speed and we're going to land. Now, right at the point of touchdown, see they heat up and they're white hot. You can also see the hottest areas of the vehicle, leading edges of the wing, leading portion of the nose. They're all about 240 degrees Fahrenheit. So the thermal protection system was critical. That's what was damaged on Columbia when the accident occurred. So they weren't able to provide that atmosphere re-entry heating. And then you're back on the ground. You feel kind of strange. So you're about to see, they all want to get a picture, and then we're all like, okay, we're out of here because we're not feeling very good. You grow in space, by the way. The spine elongates. I grew about 2. Normal. So we can talk more about that later and what happens. All right. Anybody know where this is? We're going to play Where Are World Are You? Any guesses? In space. Absolutely correct. That was an awesome answer. We are in space when we took that picture. Touchdown, Houston. This is Houston, where we live and work and where our families are. The coolest thing in the world is to fly in space and look down, essentially at your home. Now, you don't see it for very long because you're traveling 5 miles a second, so you got to get all prepared and know that you're about to transit over Houston and have a fairly long lens. But you can actually, from space, with a long enough lens, we had an 800 millimeter lens here, we were able to pick up many of the major highways around the Houston area. Any guesses where we are now? I heard it over here. Earth. Earth is correct. Very good. And I heard very specifically that is Florida. So where we launched from. So why are we seeing You know, we're seeing Houston, we're seeing Florida, right? I'm going to show you some other images. Because as we orbit around the Earth, what's the Earth doing underneath us? It's rotating, so we don't fly over the same point. Now, this mission was flown at an inclination of 28.5 degrees. 28.5 degrees happens to be where the Kennedy Space Center is. So we basically head due east out of the Kennedy Space Center when we leave town. And that takes us on an orbital trajectory, essentially between 28.5 degrees north, 28.5 degrees south. So any part of the world within that region we're going to see. The International Space Station is at 51.6 degrees. It is at 51.6 degrees, which is basically out of the Kennedy Space Center, right up the east coast of the United States, because elements were launched out of Kazakhstan, right? Out of the Baikonur Cosmodrome in Kazakhstan. And so we launched the International Space Station into a higher inclination orbit. All right, let's take the one on the left first. What's it look like to you? You know what it looks like to me? It looks like a seahorse. Anybody know what landmass looks like a seahorse? It is not the UK. Hawaii? It is not Hawaii. Japan? It is the Galapagos Islands. Very distinctive. How about the picture on the right? Anybody know where we are there?
International Space Station.
That is the Sinai Peninsula. I heard it over here, right? So you see the Red Sea, the Mediterranean Sea, the Sinai Peninsula there in the middle. Orbital sunrise and sunset. So we're traveling around the Earth 17,500 miles an hour, Mach 25, 5 miles a second. We go all the way around the Earth every 90 minutes. So half that time we're in daylight, half that time we're in darkness. So we see multiple sunrises and sunsets each day. On my first space flight, I decided if I was going to concentrate and become really good at one thing, it was going to be to take pictures of orbital sunrise and sunset. And the good thing is you get multiple attempts every day to take these pictures. But it's right at sunrise and sunset where you really get an appreciation for how small the atmospheric band is that protects the Earth. And I think if there's one universal perspective for all astronauts and cosmonauts, it's that we realize how fragile our planet is and how we all have to protect our planet. And so I think those of us that maybe weren't environmentalists before we fly in space, we certainly are when we come back. Because that thin band, when you view it from space, is incredibly thin, and that's what keeps us safe as human inhabitants. I mentioned some of the pictures that came back. This one, and they give them fancy names, right? The first thing that they do is they take the data coming back, and the Hubble Science Institute does this. They take the data coming back from the telescope and they transform it into imagery. This one is called the MICE, right? So you can see this one is about 300 million light years away. And look at the resolution coming back. Love this one called the Tadpole Galaxy. Again, this one's about 420 million light years away. This one's called the Cone Nebula, right? About 2,500 light years away from Earth. So our knowledge of the universe, our insight into planetary bodies and into the universe has so been extended by the Hubble Space Telescope and the incredible imagery that's sent back. Like I said, when I got to pick, the first thing that occurred to me is I haven't been in a classroom yet in America that people hadn't either been familiar with the Hubble Space Telescope or seen imagery from the telescope, and I really wanted to be a part of extending its mission. Here's another one. This is the Omega Nebula, or also known as the Swan Nebula, about 500 5,500 light years away. All right, so what we're going to do now, pretty good on time, now's your chance. I call this the Ask an Astronaut Anything phase. So for those of you in the room, you got two ways you can do this. You can quickly pull out your phones. They're probably out already. I already know that. Right? And you can type in your question. You can upvote a question like, yeah, I got that same question. Or you can just raise your hand and we'll do the best. For the online folks, you can either use Slido or through YouTube, how you've been asking questions. So what questions do you have? You can ask an astronaut anything.
Just before we proceed with question and answers, first of all, thank you very much for this very nice presentation, and I would like to mention, yes. I would like to mention that Professor Kerry Gregg donated the entire honorarium for this lecture to the outreach program of Physics and Astronomy Festival. So thank you very much again for that. And now, I also would like to point out that Professor Yerahimova, who is actually in charge of the Physics and Astronomy Festival, she's standing right there, because of that also will have more resources for Physics and Astronomy outreach programs. So thank you very much. Now it's time for questions.
All right, who's got a question? All right, I see one up there.
Would you recommend to other people, like, to experience what it's like to be in space? Should they try and achieve that goal to get in space?
Okay, somebody asked, would I recommend flying in space as an experience to people? Oh, you bet. Okay? I think our planet will be a different place if we could send leaders into space so that they could experience that same view that we have as astronauts, this universal perspective of the world, knowing that, you know, we all are inhabitants of Earth, knowing that we need to cooperate, we need to collaborate together, hopefully as peacefully as possible. You know, flying with a Russian cosmonaut on my third flight, as I did, was one of the most incredible experiences that I had. Because the first segment of the International Space Station was actually built in Moscow. And we made multiple trips over to Russia. And most of the folks, most of the U.S. crew members on that flight, 4 out of 5, were military astronauts. Right? We had astronauts in the Marines, astronauts in the Air Force, and I was in the Army. And when we'd all come into the service, you know, part of our mission was studying the Russian forces in case we were ever engaged in a conflict with them. And so here we were in the late 90s, peacefully working together for this incredible opportunity to put an orbiting laboratory in space. And I'll tell you what, I'd much rather be working collaboratively than engaging in you know, non-peaceful efforts. So I think if people could experience that view. I know when I came back from my first flight, people told me, you've changed. You know, and some of it degrades over time. Like when you first come back, and like if you're 5 minutes late to a meeting, you're like, the grand and universal perspective of life, that has no meaning at all, right? And you lose that part over time, right? But there are certain elements, like knowing how fragile our planet is, that will never leave you. And there are certain songs that I hear, there are certain movies that I see, IMAX movies, and if you show IMAX movies that were filmed in space to a group of astronauts, I mean, you almost hear people, you know, kind of sniffling, and because it takes you back to that experience. It's all like mentally transported back to that experience. So absolutely, if people could experience that, I think we'd all be better off. Next question.
What's your opinion on emerging space research and exploration done by the private industry?
Okay, private space ventures. They kind of come in all shapes and sizes, right? We got some that are suborbital flights, right? 15 minutes, you get a glimpse of what it's like, and then you're back on the ground. if you don't know, we have a private company launching people to the International Space Station for 2 weeks. It's led by a former astronaut. We call him Mike L.A. And Mike L.A. is going to take 3 non-professional astronauts into space. I believe it's scheduled for next week or within the next couple upcoming weeks. And they're going to fly on the International Space Station. So, again, it gives them that experience. You know, as a professional astronaut, quite frankly, you know, it's going to be, please don't get in the way of our professional jobs and the science that we're doing. And the International Space Station, if you don't know it, is as big as a football field. So that's pretty easily done, right? For people kind of stay out of the way of the maintenance that we have to do on the space station. Certainly the science that we're performing. It is a designated U.S. national laboratory. So it is one of our U.S. national laboratories. It's a national asset, and we're doing great things from a science perspective in space. A lot of the science that we're doing is the effects on the human body. Mark Vande Hei just landed this week after serving on orbit for almost a year. He set the record for U.S. astronaut duration. Why are we keeping people in space for a year? Because a mission to Mars is going to be about 2 years long. And really, we only have a handful of folks that have flown over 6 months in space. And what happens in space is bone mineral density loss, bone density loss, bone structural changes, musculoskeletal changes. We see swelling in the eye, right? We call it SANS, Spaceflight Adaptive Neuroocular Syndrome. And because we know that we're seeing physical changes in the eye, because the first thing that happens as soon as you get to space is a fluid shift. Fluid shifts from your lower body to your upper body. Now your body is not used to really that fluid shift mechanism, and so it detects instead that you have fluid overload. And it starts to suppress a hormone called antidiuretic hormone. So it suppresses antidiuretic hormone, which means you diurese. And so from an Earth-based perspective, you're about 10% plasma depleted. You're about 10% dehydrated compared to what you would be here on Earth. But because of this fluid shift, right, it's going, more fluid's going towards your head. It's putting more pressure on the back of your eyes. So we're seeing globe flattening. We're seeing structural changes in the eyes that never resolve when astronauts come back in some cases. And then because we saw these changes in the eyes, we thought, what's happening to the brain? So we now have evidence of brain swelling in extended duration spaceflight. What are the ramifications for that long term? Quite frankly, we're not sure. And we need to answer these questions before we intentionally send people like on a mission to Mars for 2 years. So we fully have to understand those mechanisms. Great question. Let me take one from this section and then I'll come back. Yes? Yes?
Erin would like to work at NASA and she's doing her concentration in mathematics, but our school's a lot smaller, so there's a lot of people to ask those questions in front of. So we talk to our students all the time, like, learn math, learn data analysis, know your computer science, but what other skills are we not preparing them for? Because you talked about diplomacy, you talked about politics, there's teamwork there. So how do so many of these kids in here stand out and learn beyond the classroom?
That's an excellent question. So the gist of the question was for kids that ultimately either want to be an astronaut or come work at NASA, obviously having a degree in one of the STEM fields. And NASA used to keep a list, quite frankly. When I applied to be an astronaut, there was a list of 200 different degrees. So now they just say anything in science, engineering, math, computer science, right? Any of the STEM disciplines. So the fact that you're here today, nothing makes me happier in the world to know that our country's in good shape, that students are still interested in STEM. But you're right. There's those things that we as engineers refer to as soft skills, and even though we call them soft skills, they're harder than learning mathematical equations. And one is teamwork. I always tell my students, engineering is a team sport. I've never worked on a single project in my entire career by myself. I've always worked with people sometimes from other countries, other cultures, other disciplines. We all come together, aggregate our skills to handle some of our globe's toughest problems, right? Diplomacy, learning to respect other cultures, maybe even learning other languages so that you can communicate with them. So those are all equally important. And so the more we can introduce that at younger ages within our classrooms, and that looks like project work, right? You don't get to pick your teammates because I've never got to pick any of my teammates, whether it's in the United States Army or at NASA, right? So learn to work together to achieve our common goal and respect each other and what they can contribute in their own unique ways. And so I think at every level, I know I do that in undergraduate and graduate classes, and that not only enhances the teamwork and communication, all those other skills that we need in STEM, but it also makes learning, right, very hands-on oriented. And I always tell my students, I don't use any notes to give a talk like this because I lived it. So if you live that project work, you know, you're going to learn it because you lived it. So let's make learning as engaging and as hands-on. The things you're going to see today, right, are very memorable events. And those really make impactful statements and really hope to help to bring, you know, what does this really mean? What does this concept mean? Well, it means that these two chemicals result in this kind of explosion and boom, here it is, right? Something I'll never forget. So that's a great question. All right, so for those of you that, all right, here's one. I will pick this one. I'll pick two out of here. What barriers did you face along your career journey as a woman at NASA? At NASA? None. United States Army? None. So does that mean I was never discriminated against? No, I was, and it was very memorable, and I'm going to share it with you for a reason. Now, because of the world's political situations today, I'm not making a political statement. I am just saying the facts. So on my third mission, we were in Kazakhstan at the launch complex, getting ready for the first launch of that Russian segment of the International Space Station. My job on the mission, one of my many jobs on the mission as flight engineer, was to be the fix-it person, right? So if anything failed, I was going to remove and replace it or repair it, and you know, I had studied all that. So I was responsible not only for the US system, but the Russian system as well. So we were in the actual spacecraft, all was on the ground. We were looking at pieces of equipment. And I looked at this one piece of equipment, and now the company had, in its past, only built spacecraft for unmanned spaceflight. They've never built one for human spaceflight. So I looked at this particular box. It happened to be a battery charged discharge unit. And I wasn't quite sure how to get it out of its place because there was a thermocouple bonded on the side, the electrical cabling had all been connected together. And I asked a few questions and nobody could answer my questions. And they said, in the afternoon, we will bring in our chief designer and he will answer your question. Great. So my Russian was not that great. So when they brought the chief engineer in, chief designer, we had interpreters there. So I asked my question, they translated it, he answered, and then everybody just had kind of one of these looks. And I said, what did he say? He said, a woman will not touch my hardware. And I thought it was a joke, because I'd never, ever heard that. And so I started laughing, and I said, tell him if you can't trust a US American pilot, and an astronaut who's already flown a couple times, who can you trust? And he repeated, a woman will not touch my hardware, and he turned and he walked away. Now at that point, you know, I was training for this fantastic mission to go put up the first piece of the space station. I've flown in space before. I have 4,000 flight hours in the military, and I had a PhD. And in one brief comment, he reduced me pretty much to nothing. I was not feeling really good about myself. And in fact, we were supposed to have this big joint dinner that night, and the guys came and knocked on my door and said, I don't think I want to go. And they kind of made me go along with them. But I know how devastating that event was for me, even though I'd accomplished some things in my life, you know, at least within my professional domain. And so I share that story with you because never, ever, ever make somebody feel that way because of their gender or their culture, right? Or where they're from. Because everybody, and especially in the United States of America, there are no boundaries on what you can achieve in your career. And if you ever get that kind of comment, I know it's going to hurt. I've been there. I mean, I'll be quite frank, it reduced me to tears when I was out of sight of the rest of the males I was flying with. And you know what? I thought, I'm going to show them. And the end of the story is, when the Russian segment launched, guess what piece of equipment failed? I'm not making this up. I am not making this up. So they sent a replacement unit over for us to fly on the shuttle 2 weeks later. So we took it up to space, and then came the day where I was going to, theoretically, I was going to be the one, but I assumed that the Russian cosmonaut on our flight, who was male, was going to do this. And I looked at the commander and I said, I assume I'm just going to help Sergei do this, right? And he said, oh, no. You are going to do this, and I'm going to film it, and I'm going to send it to the ground and say, this one's for you. I know that sounds like a made-up story, but it is not made up at all. Absolutely true. All right, what's your favorite food? Believe it or not, creamed spinach, right? To make matters worse, I would sometimes eat it for breakfast. So on shuttle, we had primarily dehydrated food because the shuttle generated electricity using cryogenically stored oxygen and hydrogen. Cryogenically stored, cooling them down to the point where those normal gas states are liquid. You can store them in tanks. The combination of oxygen and hydrogen make what? Water, H2O. So in fact, we made so much that we would have to jettison some overboard every few days. And it was interesting because when we did that and we'd shoot it out a port of the side and we could film it out the window, it would immediately sublimate into ice and it would look like we were flying in a snowstorm. So it was really cool. But we would fly these dehydrated foods. So believe it or not, dehydrated spinach was my meal of choice on orbit. Let's see, how about one more in the room? Way in the back. Go ahead. Red shirt. Can somebody repeat that? When will we be able, well, believe it or not, people have been living in space all the way back since 1999 on the International Space Station. So there has not been a day go by since 1999 that you haven't been able to look up into the sky and know that people were orbiting the Earth in the International Space Station. So we already have that capability. Now, how about a mission to the moon? Who knows when that flight is, right? It's sitting on the pad right now, ready to go. So we're going to launch, and that one's an unmanned test flight. This vehicle is huge, it's as big as the Saturn V that went to the moon. That vehicle's sitting on the launch pad at the Kennedy Space Center right now. We're getting ready to launch a mission back for lunar purposes as a predecessor into sending people back to the moon in the next few years. My class patch, if you can see it, astronaut class of 1990, has the moon and Mars on it. Then President Bush said, we're going back to the moon and onto Mars. And we thought, wow, we're the astronauts that are going to do that. And then it didn't happen. The International Space Station, that was great, but we really are going back to the moon and onto Mars. So I can now definitively say that there is somebody in a classroom in America today who will put footsteps on Mars. I am absolutely convinced of that. All right. One more or no? Sure. Okay, let's do one. How about a young lady right here?
How far has you gone into space?
How far have I I gone into space? I have gone 350 miles up into space. Now, what does the moon look like from that perspective? Not a whole heck of a lot different than it does here on Earth, right? The moon's roughly 25,000 miles away, but you're not looking through the atmosphere. And so the really cool thing about being above the atmosphere, there are literally billions and billions and billions of stars out there. I've seen them, right? So on a very starry night, in an area of the country where there's not many lights, you think you're seeing a lot of stars, you should really see the view above the atmosphere. It's absolutely phenomenal. I want to thank you today for providing such an engaging experience. I want to thank you for coming back to the Physics Festival in person. For the teachers in the audience, I want to leave you with this. The way I perceived that I got to the launch pad was carried on the shoulders of the teachers that enabled me to do that. That's in part why I came to a university to teach, because if it weren't for teachers, I wouldn't be standing here. I wouldn't have done the great things that I did. So for the students, your teachers are really smart. Listen to them, right? And for the teachers, never underestimate the impact that you have on a child, because they're capable of achieving great things in this country, and I thank you for your investment in the STEM personnel of our future. So thank you very much. Hope you have a great time at the Physics Festival, and thank you.
Thank you very much. Thank you, and thank you everyone for participating in this event.
Here are those Zoom room links as promised. This is your chance to interact with amazing physicists and ask them anything you want. Just visit the link on the screen or scan the QR code. We hope to see you back here at 2:30 p.m. Central for our grand finale, the 5-barrel depth charge with 1,000 plastic balls. Following that will be our Mitchell lecture from Professor Alex Filipenko, starting at 3 p.m. Central Time. Now go! Join us on Zoom.
Testing reboot. Testing reboot.
Is it good or is it? Yeah, it should be better, but I don't think I can adjust the dB down anymore here. Daylight. There we go.
Howdy! Alright, y'all, so we're gonna kick this off the only way a fight Texas Aggie way. Fight Texas Aggie knows how. So pass it back, Gag. You'll do this. Do exactly what I'm doing. There we go. Alright. Pump it, Gag. Go right here. Right here, and you yell, okay? 1, 2, 3, 8.
last reminder that you can enter for a chance to win a bundle of science goodies like a t-shirt and more delivered to your door. Visit our website at tx.ag/science giveaway. There's a link for that in the video description. Now, let's take a short break as we get ready for our second speaker and final speaker, Alex Filippenko, with his Mitchell lecture, Dark Energy in the Runaway Universe.
Welcome to the 14th Mitchell Lecture here at Texas A&M University. This lectureship has been endowed by the Mitchell family, George and Cynthia Mitchell, and the Mitchell family, and we're very, very proud to be able to bring this festival and these speeches to all of you. We always invite a very prominent scientist or engineer, or in the case astronaut, to come and give these talks. And I'm particularly happy to be able to present Dr. Alex Filippenko. He's a longtime colleague and a friend of mine, but he is one of the most famous astronomers in the world. If you go on to TV tonight and turn on Netflix and go to the program The Universe, you'll see Alex on The Universe. He's all over television. He's one of the most sought after speakers about explaining astronomy in the world. But what's amazing too is besides being a great educator, he's won awards for being the best educator at UC Berkeley. The students have voted him many times as being the best professor at UC Berkeley. He's also one of the most prominent astronomers in the world. He's a world's expert in cosmology and also in the study of exploding stars called supernovae. And he will tell you a little bit about our universe today. And what you should realize is that much of what he talks about today, he has helped discover. So we both have a phenomenal educator, but also a phenomenal research astronomer. There are very few astronomers that combine both of them into one person. So without further ado, I'd like to introduce Dr. Alex Filippenko from the University of California at Berkeley.
Oops. This thing fell. Well, howdy. Howdy. I learned that from this morning's lecture by Nancy the astronaut. Great. One of my ambitions is to learn something new every day, so howdy. Anyway, it's such a pleasure to be here. Thank you, Nick, old friend and colleague, for that very warm introduction. What a fantastic day the physics and engineering departments and astronomy have put on in this festival, huh? Hasn't it been fun? All these, let's give them a big round of applause. Yeah. What a great thing. I was taking photographs during the day. I'm going to steal some of these ideas and bring them back with me to UC Berkeley. And we have some, off-campus visiting days of this sort, but the number of different demos and interesting, cool things here was just phenomenal. And how about that big explosion we just witnessed there, right? How many of you got a little colored ball, right? Come on, lots of little colored balls, A few minutes later, you couldn't find a single one of them there. Anyway, so thank you so much, Texas A&M Physics and Astronomy Department, for the invitation. I want to also thank Ram and Angela Galindo, who are my hosts during my several-day visit here. I see them in the back there. And Ram actually was the one, I think, who got the idea rolling to invite me here. And although Nick and I have known each other for many years, I think Ram said to Nick, hey, why don't you have Alex speak at this festival? So thank you, Ram and Angela. Anyway, it's a great pleasure to be here. I want to tell you something interesting about the universe. So let's go ahead and put up my first slide here. Dark energy and the runaway universe. Okay, very good. So I'm an astronomer, an astrophysicist, but today I'll be speaking about cosmology, that subset of astronomy that deals with the structure and evolution of the universe as a whole. So we're interested in some of the grandest questions. Is the universe finite or infinite? What is its shape? Where the hell did it all come from, basically? And the cave people were probably asking that question as well. And here we are, millennia later, and we're asking the same question. Where the hell did it all come from? If you'll pardon my French, I didn't think that there'd be so many kids here, but, whatever. It's not my cartoon, but okay. So, Time magazine, when did the universe begin? They have a lot of subscriptions, but national magazines like this sell a lot from newsstand sales. And they won't have as a cover story a story that they don't think sells. But astronomy and cosmology in particular sells. This is a big time story. Get it? A big time story. When did the universe begin? Right. Another one, how the universe will end. This was actually written 21 years ago about the work that Nick and I and our teams did. Back then, 20 years ago, we thought we knew how the universe would end. Here we are, 2 decades later, we've done some more research, and now we're not so sure how the universe will end. But in any case, they should have had a question mark there. Peering deep into space and time, scientists have just solved the biggest mystery in the cosmos. Well, maybe, maybe not. We'll see. Cosmologists are interested also in galaxies, the basic building blocks of the universe. They consist of 100 billion stars, gravitationally bound together in these gigantic structures called galaxies. We live in one such structure, the Milky Way galaxy. Our sun is one of 100 billion, or even modern estimates, 400 billion stars. So the stars that you see out there are like suns. They are distant suns. And they're gravitationally bound together. They look like this. Some of them have different shapes. This is not our own Milky Way galaxy. If anyone has a photo of the Milky Way galaxy taken from the outside, see me after the presentation. I would like to purchase usage rights from you, okay? But we're like a mouse in the maze. So it's actually easier to see the structure of other galaxies than to see the structure of our own galaxy in some ways. And, our own galaxy is not alone. Here's one of my favorite photographs from the Hubble Space Telescope. This is the Hubble Ultra Deep Field. It's actually only part of it. The telescope basically stared at the same part of the sky for something like 10 days or 2 weeks over the course of time. This is a tiny fraction of the sky. Imagine a grain of sand held at arm's length. Imagine how small that looks. That's the fraction of the sky that is covered in this photograph, and it consists of thousands of galaxies. I can count them. 1, 2, 3, 4, 5. It would be pretty boring for you if I spent my hour counting galaxies, but you know what? It's a pretty cushy job. They pay us to sit around and count galaxies. What could get better? Anyway, there's several thousand in this grain of sand, and we've taken many such pictures over the sky, and so this is representative, we know that. And so within the realm of the Hubble Space Telescope, there's more than 100 billion galaxies, each with tens or billions, in some cases trillions of stars. So it's a big universe out there, but this is only the observable part. We have good reasons to think that our observable part of the universe is a small fraction of all that there is. So this is what cosmologists study, and so I feel very, very fortunate to be in this field. Well, let's go back about a century to Vesto Slipher, an astronomer in Arizona. And he studied clouds of gas out there called spiral nebulae. This was before they were known to be external galaxies, island universes in a sense. Some astronomers thought that they were clouds of gas in our own galaxy where new stars are forming, like the Orion Nebula. And he looked at the light from these spiral nebulae and passed the light through a prism or a device similar to that, producing a rainbow. And what he noticed was familiar patterns of dark lines. Those are produced by various chemical elements in the outer atmospheres of stars. Spectroscopists are trained to recognize those patterns. And he saw the same patterns in a galaxy, or a spiral nebula, I should say, as in collections of stars in our own galaxy, but they were shifted toward redder wavelengths, longer wavelengths of light. And this could be interpreted in terms of these spiral nebulae moving away from us. It's related to, but not exactly the same thing as the Doppler effect, which you can hear when a siren gets coming toward you. The pitch sounds high, and then it's going away from you. It sounds low. That's because on its way in, the waves are being squished together, so it's ee type pitch. And when it's going away, they're spread apart. So it's sort of ooh, like that. So you could say that these things are moving away from us, but the distances were not known, so Slipher couldn't really do much with this information. Enter Edwin Hubble, much better known astronomer, after whom the Hubble Space Telescope is named, and he used the 100-inch telescope at Mount Wilson Observatory, which is above the Los Angeles basin. And he took pictures repeatedly of some of these spiral nebulae. And in particular, he took pictures of the Andromeda Nebula, known as M31. And he was looking for stars that occasionally undergo a pretty bright outburst. They're called novas, new star, nova stella. They're actually an old star that has a surface nuclear explosion occur. But he was looking for them, and he marked them with these N's. And then there's one at the top there that he marked with an N, and then he crossed it out and marked it with var, variable, because he noticed that that star was visible in some previous photographs, and then it brightened, and then it faded, and then it brightened again in a way that was not characteristic of a nova, but rather of a variable star. And here's a more recent Hubble Space Telescope picture of that first variable that he discovered. But he discovered a bunch of them. And he could tell what kind they were because they were a type of variable star that was well known in our own galaxy. It's called a Cepheid variable. You can see its brightness versus time. It brightens reasonably quickly, and then it declines more slowly, and then it can brighten again and decline. And this one has a period of little over 5 days. Other ones might be as short as 1 day. Others might be 100 days, okay? But these are very luminous stars whose properties are so distinct that you can recognize them pretty much anywhere where you can see them in the universe. Not all stars are exactly like our sun. There are different varieties of stars. So you need to know what kind of star you're looking at. You could tell that this was a Cepheid variable. They're very luminous, powerful stars. And in fact, Henrietta Leavitt in 1912 at the Harvard College Observatory had calibrated how powerful these types of stars really are. And they're typically like 1,000 times more luminous than our sun. So you could see them as individual stars in the Andromeda Nebula. But they looked faint. And so Hubble reasoned that they must be very, very far away, because it's just like car headlights. You look at a nearby car and you say, whoa, those are pretty bright headlights. And then you look at cars that are more distant and the headlights look dimmer, and even more distant, they look still dimmer. And your brain is doing a little calculation. It's called the inverse square law. There were demonstrations of that among some of your little things throughout the day here. But you know, you don't have to write down the equation on a notebook and stuff. You're just driving along, and you've become accustomed to this kind of thing. You do it almost intuitively, almost instinctively. I would argue if you're not good at doing this sort of thing quickly, you shouldn't be driving at night, okay? But cars, stars, it's the same thing. If you find a star whose true power you know, kind of like a car headlight at a distance of 2 meters, that allows you to calibrate it. Well, then you can look at other such stars, other such headlights, and figure out how far away they are. And the Cepheid variables in the Andromeda Nebula were so faint that they were clearly outside any reasonable boundary of our Milky Way galaxy. Moreover, the spiral nebula, Andromeda, looked so big in the sky, it's actually bigger than the field of view of typical binoculars, that given its apparent size in the sky, several full moons actually, and given its distance, which we now know to be 2.5 million light years, the distance light travels in a year is a light year, it's 6 million miles. Okay, try that at 55 miles an hour or even the higher speed limits that tend to exist in Texas, okay? But this is a big state, and you have a large amount of room, of mostly empty roads, between the major cities, so I guess your speed limit might be higher here. But anyway, 55, 65, 75, I don't care. It's going to take you a long time to go 1 light year, 6 trillion miles. This thing is 2.5 million light years away, and then you can figure out that it's physically really big, at least as big as what was thought to be for our own Milky Way galaxy. So this was clearly an external galaxy, an island universe, going back to some of the philosophizing of Immanuel Kant. He had that idea, and as did others even several centuries ago. But here, Hubble figuratively expanded our view of the universe by demonstrating that the spiral nebulae are external galaxies. Okay, already a great discovery. But there was more to come. By getting the distances through Cepheid variables of these galaxies and using Slipher's speeds, he noticed a very interesting thing. Oh, I forgot to start my timer, so I don't know where I am. Is there a clock anywhere here? Darn it. Oh, up there. Okay, good. I always have a little cheat sheet telling me where I should be at any particular time, then I forgot to start my timer. How long have I been going? It's 3:15. Okay, so I'll add 9 minutes to whatever I have here. Okay, so where should I be after all? Yeah, okay. All right, now I'm going to be very confused for the... By the way, I've given very few talks in person up until just a couple of months ago when we started in-person classes again at Berkeley. But it's been a weird 2 years, and thank you all for coming here. And it's just such a weird experience lecturing in person again after all these Zoom calls. Anyway, he found that the nearby galaxies are moving away from us pretty fast, but the more distant galaxies that look fainter and smaller in the sky are moving away from us even faster. So they're all moving away from us, but at a given time, right now, the more distant ones are moving away faster than the nearby ones. And this turns out to imply an expanding universe. Hubble himself resisted that explanation for quite some time because it was kind of a radical idea. The universe is expanding, but now we embrace this as being the most reasonable explanation, and there's a lot of evidence for it. And it's not that the galaxies themselves are expanding. They're gravitationally bound, and solar systems are gravitationally bound, and planets are bound, and you're bound by electromagnetic forces, okay? So it's the space between galaxies or even clusters of galaxies that's expanding, okay? So not everything is expanding. A lot of times in the press they get this wrong. Sorry I'm late, but you know how the universe keeps expanding. No, that is not a valid excuse because the distance between your home and your office did not expand, okay? Here's another one. If the universe and everything in it is expanding, how come our budget gets shrunk all the time? People glibly say everything's expanding, but most things are not locally, okay? It's starting from about 10 million light years, that's a good rule of thumb. Beyond that distance, things are moving away from you, but most things we know of are a lot closer than that. Okay, well, with today's telescopes, Hubble, Lick, Keck, others, there's the University of Texas McDonald Observatory here in Texas. We figured out how quickly the universe is expanding. And that's just a number. It's an interesting number. I'll get to it near the end of my presentation. But initially, I want to point out that the number should be changing. And, I have an apple here somewhere. Where did my apple go? Oh, my goodness, I need my apple. You can't give a talk about gravity without using the proverbial Newtonian apple. I found it, okay? So you go back to Newton, right? And Newton supposedly had this apple fall on his head. That's apocryphal. But he did apparently see apples falling from trees, and he wondered whether whatever it is that's causing the apple to fall from the tree is somehow related to the moon being in an orbit around Earth, okay? So he tried to unite terrestrial phenomena and celestial phenomena, which back in the 17th century was a tremendous, intellectual leap, really, because people thought that out there was governed by the gods and all that, and here, whatever. Why should they be related? But he found through his law of universal gravitation and his laws of motion that you could understand the moon as falling continuously toward Earth, but it also has a sideways motion, and those two motions end up giving you an orbit. So he did indeed unite celestial and terrestrial phenomena. But you all know that when you toss an apple up, the mutual gravitational attraction between it and the Earth slows it down. So in a similar way, all these galaxies should be pulling on each other, slowing down the expansion of the universe, right? There's stuff in galaxies, visible stuff. The universe, though expanding, should be slowing down. And not just because of the visible matter. Turns out that beyond the visible matter, there's a lot of so-called dark matter in galaxies. Indeed, 85% of the matter in galaxies is dark. And that goes all the way back to the 1930s. One of my heroes, Fritz Zwicky at Caltech, who looked at clusters of galaxies. Here you can see a very famous cluster of galaxies, and he measured the motions of the galaxies and showed that they're moving so quickly that the cluster would rapidly become unbound. The galaxies would leave each other unless there were extra gravity beyond the gravity associated with the visible stuff. Okay, he had a number of explanations. One of them was that there's invisible stuff helping to hold them in. And you might say, well, if there's only one cluster, maybe it's the chance alignment of galaxies in the night. But there are lots of clusters, and they all seem to be bound, so they weren't just, galaxies flying past each other in the night. They were real structures, and now we have other evidence for there being lots and lots of dark matter. There are these little wispy things that you see here, which are gravitationally lensed images of background galaxies. Gravity actually causes a warping of space and time, which makes these galaxies look like little arcs and stuff. And there's lots of other evidence for dark matter. But, Zwicky wasn't believed in the 1930s. He was brilliant, but he was also sort of abrasive and arrogant. And he didn't think much of the intellectual capabilities of his Caltech colleagues. And Caltech in Pasadena, the California Institute of Technology, is quite a brainy place with a lot of big egos. And they did not take lightly to his opinion of them. For all we know, he's showing you what he thinks of their typical brain size. Right now, I don't know that that's what he's thinking, but he might be thinking that. He is on record as having referred to his colleagues as spherical bastards, because, they're bastards any way you look at them. And a sphere is the only shape that looks the same from all directions, right? I am not suggesting you refer to your friends and relatives as spherical bastards. You will, and again, pardon me, in case the young ones haven't heard that term, I apologize. But anyway, But he was right about this, that there's this dark matter. And I kind of like, I think he was an amazing fellow. So people ignored him, okay, until the 1970s when Vera Rubin and some colleagues came along, and they studied the rotation of spiral galaxies and found that they're rotating so quickly that they too would fly apart unless there were dark matter in excess of, in considerable excess of the visible matter, the visible stars and gas that you see. So we know that there's a lot of dark matter as well as visible matter. And what we don't know is what the dark matter is. And, every decade I hope springs eternal that we'll figure it out. We don't know what dark matter is. It could be black holes. Black holes are regions of space where matter is compressed so much that nothing, not even light, can escape. That's a whole separate talk. They're fascinating objects. We know that some of the matter that's dark is dark matter, but not most of it. Indeed, we think most of the dark matter might be little tiny particles left over from the hot, fiery, dense birth of the universe that we call the Big Bang. There are maybe lots of little subatomic particles flying around left over. WIMPs, that's short for weakly interacting massive particles. WIMPs versus machos. Machos are things like black holes and dead stars and things like that. So for a long time among astronomers, it was the WIMPs versus the machos. Well, there aren't enough machos out there to explain most of the dark matter, and people have been looking for WIMPs for a long time and still haven't found them. That doesn't mean they don't exist, but their stock is kind of going down. So, among the youngsters here, if you're told someday that we know everything there is to know about the universe, you tell them, what about the nature of dark matter? And even more so, the stuff I'll talk about next, the dark energy. So anyway, you've got visible matter and dark matter, and they're pulling on each other. That should slow down the expansion of the universe. Now, if the universe is dense, that is, if there's a lot of material in a cluster of galaxies there and there, the slowing down will finally reach a stop, and then there will be the reverse. And instead of a big bang, you could have a big crunch. Or you could say Big Bang Gnab Gib, which is Big Bang backwards. Okay, get it? Big Bang Gnab Gib. Right? That's Big Bang backwards if you write it down. So if you were living in a dense universe and lying on your back watching the galaxies, you would say, oh, they're getting smaller and fainter. I live in a well-behaved universe. But then you notice something peculiar going on, and now you're getting kind of nervous, and then it's goodbye, cruel world, because the universe collapses in on you. That's one possible fate. But if the density, the mass per unit volume of the universe isn't very high, then it would be sort of like if I were to throw this apple at a speed greater than Earth's escape speed. I can't do that. That's 11 kilometers per second. And there's the technical difficulty of a ceiling here. But, rockets do that. And here in Texas, you launch rockets and stuff. That's what they do. They go at more than about 7 miles per second, and they can escape. And it's not that you cut off gravity between Earth and the rocket. It keeps slowing down. It left Earth with a speed big enough that it won't come to a stop and it won't come back. So if you were living in a low-density universe, you would see the galaxies getting smaller and fainter with time forever. And it would end up not in a hot, dense, fiery, big crunch, but eternal expansion, cold, dark, dilute. Those are the two possible fates of the universe. And cosmologists want to know, what will be the fate of the universe? Will it give you a better toaster or a pacemaker or something tomorrow? No, it won't. But it's an interesting question. It's like a mountain that we want to climb. It's there, so you want to climb it. But there are other things. There's the practical spin-offs that you never know about for sure. Quantum physics, you fast forward 1 century, we couldn't live today without all our little devices and things. Even general relativity, Einstein's harebrained theory of the warping of space and time. GPS relies on physicists and engineers having understood general relativity. Otherwise, GPS, with all of its commercial and military applications, wouldn't work. So you never know what practical spin-offs there might be from pure research. And secondly, these kinds of results excite the kids. Kids here, are you excited? Does some of this stuff sound interesting, right? Most of you don't need to become professional astrophysicists. That's okay. There's only a limited number that we need in the world. But no, I'm true. It's not that I don't want more astrophysicist friends, but come on, let's be practical here. But you're more likely to go into STEM fields and into areas that are more immediately beneficial to society, like engineering, applied physics, medical physics, computer science, things like that. So it's kind of like the dinosaurs. Cosmic things excite kids, and they're more likely to go into STEM fields. We're hoping that many kids here will be excited by the festival that you witnessed today. So we would like to know, all right? And how do you go about figuring out what the universe will do in the future? Well, go back to the Apple example. That's why I needed the Apple. If I were to measure its speed at many different times and see that it's been slowing down a lot, then I can predict that it'll stop someday and come back. Whereas if I measure its speed at different times and it's not slowing down a lot, then I can predict that it'll keep on going forever, all right? So that's the idea. We've measured the current rate of expansion, compare it with what it used to be. And you might say, well, we live here and now. How can we go back in time and see what it used to be? Does anyone have any idea of how astronomers can see things back in time? Anyone? Light. Yeah, what about light?
The light is set speed. So
there you go. The speed of light is not infinite, so it takes time. What's your name? Ty. Ty is maybe 30 or so, 40 feet away from me. Light travels a foot per nanosecond. So I'm seeing Ty as Ty was 30 or 4 billionths of a second ago. Not now. Ty may not even exist anymore. Oh, Ty does. Good for Ty, okay? You see the sun as it was a little over 8 minutes ago because it takes 8 1/3 minutes for the light to traverse 93 million miles. Even the nearest stars that you see are some tens, hundreds, or in a few cases, by naked eye, 1,000 light years away. So you're seeing them as they were tens, hundreds, or even 1,000 years ago. So if you look at galaxies that are, say, 1 billion light years away and 4 billion light years away, and maybe that little blob there is 9 billion light years away, you're seeing them as they were 1, 4, 9 billion years ago, and encoded in the light, in the form of this redshift thing, how much the spectrum shifted toward the red, is information about how much the universe has expanded during the time, 1 billion, 4 billion, 9 billion years, over which the light was traveling through space from it to us. So the non-infinite speed of light gives us a movie of the past history of the universe. It would be much more boring if the speed of light were infinite. Then we'd see the whole universe as it is right now. But how do I know that this galaxy is 1 billion light years away, or 4 billion light years away, or 9 billion light years away? Cepheid variables, although very powerful stars, are nowhere near powerful enough to be seen at such great distances. So it sounds like we're hosed, all right? Or maybe not. Does anyone know what kind of an object might be visible at such vast distances? Anyone? A quasar, that's true, but they have too much of variation among how much oomph they have, how powerful they are. A supernova. Oh, someone said a 1A supernova. Well, you type 1A. You know, this talk isn't for you. You've done too much reading on. No, I'm just kidding. You're welcome to stay. A supernova. Now, what's a supernova? It's a star that blows up at the end of its life, becoming millions or even billions of times more powerful than the sun. Okay? I mean, here's one that took several weeks to brighten and some months to fade. My colleague Peter Chalice sped up the process so as to not bore you, okay? But this thing is in a galaxy of 100 billion stars at its brightest, right there. It's comparable to the central billion stars in this galaxy. Central billion normal suns. That is one powerful star, right? You might say, whoa, what if our sun does this? Well, if our sun does this, folks, sunblock of 50 just won't cut it. You'll need sunblock or supernova block of a few billion to protect yourself. But don't worry, be happy. The sun's not going to blow up. If it does, you can ask the Berkeley chancellor to fire me. You can ask the Texas A&M chancellor to fire my colleagues Nick Sunsef, Li-Fan Wang, others who work on supernovae, Peter Brown. The least of their worries will be fired, even with tenure, if the sun blows up. I'm not going to be worried about being fired, so go ahead. All right. Well, we found these supernovae, and yes, there are different types. We use the type 1As, but I won't go into the weeds here, but the 1As are very powerful, and they're nearly standard, so they're very, very nice. We found them in galaxies where we can see Cepheid variables and other such stars, traditionally, which we have used to get the distances of those galaxies, okay? So that's like the car whose distance you know. It's 2 meters away. You say, whoa, those are pretty bright headlights. You calibrate how bright the headlights are. So we calibrate the type 1A or whatever supernovae we're using by finding them in galaxies whose distance we already know. Got this? Okay, I'm aiming really high in this talk, all right? So I love this morning's talk, by the way. Is Nancy here? That was really a great talk, seeing the refurbishment of the Hubble Space Telescope, but it wasn't quite as conceptually abstract as the stuff that I'm telling you here. So sorry about that, but I hope it's amusing, if not educational. So anyway, then the whole thing is to find them in these fuzzy little distant galaxies, see how bright they look, and thus determine the distance and thus how far back in time you're looking. Okay, that's the name of the game. Find out how far back in time you're looking, and then look at other properties of the light, and that tells you, how much the universe has expanded, that kind of thing. So we want to find them far away. And if we find them far away, we can determine their distance, and hence the look-back time, and we can also measure from the spectrum the redshift, or how quickly the thing is moving away from us. Okay, and those are the two things we need in order to trace the expansion history of the universe. Those are the things we need. So how do we do it? Well, in the early 1990s, two teams formed, one by Saul Perlmutter at UC Berkeley, and in particular, he was associated with the Lawrence Berkeley National Lab at the time. Now he's a professor of physics in our department. And then Brian Schmidt, whose home base was in Australia, and Nick Sunsef, a professor of astronomy and physics here at Texas A&M, who at the time was in Chile before he came here to the Mitchell Institute. But they formed these two teams. One was the high Z team, the high redshift team, the other one the Supernova Cosmology Project. And Brian and Saul weren't always at each other's throats, and Nick and stuff. But occasionally we would meet in places like Aspen to discuss the generalities of, and even the specifics sometimes of what we were doing, being careful not to reveal exactly what it is we're doing and how far along are we, because you don't want your competition to know how far along you are. And they thought they were way ahead, Saul's team. I actually started with Saul's team, but then I switched to Nick's and Brian's team because their culture was more that of astronomers like the ones I had grown up with, studying supernovae, and we knew each other and stuff. Saul's team came more from the culture of high-energy experimental particle physics, where it's more of a hierarchical thing, and it was just not as much my style. So I switched from Saul's team to Nick and Brian's team. But I'm the one person who actually was on both teams. But we agreed that I would stop hearing about Saul's team's progress. That would have been unfair, right? I'd be like a mole or something if I... Anyway, so, but it was good. It was good to have these two teams because Both wanted to be first, so that, if you'll pardon the pun, accelerated progress in the field. Both wanted to be best. If one team is taking something into account, something subtle, and the other team is not, then that other team looks bad by comparison. And then, frankly, the result that we found was so strange that very few physicists and astronomers would have taken us seriously had there only been one team. But they came up with the result nearly simultaneously. Brian and Nick's team was first. Saul denies this, but whatever. The publication record speaks for itself. You know, sort of, if there are lawyers among you, the documents speak for themselves, right? And so, okay. So we found these things at the Cerro Tololo Inter-American Observatory where Nick worked. And it had a camera that would take wide-angle pictures of the sky. This is roughly the area of the full moon, even if the full moon is not rectangular in shape. And most of the blobs there are actually other galaxies. They're not stars in our own galaxy. They're mostly other galaxies. So you take like 50 photographs like this throughout the sky, and then 3 weeks later, you take a repeat, photographs of the same parts of the sky, okay? And then you subtract the old photographs from the new photographs. And this is all done digitally with modern detectors, so it's relatively easy to do. You know, and here there's some noise. I don't know if you can see it in a brightly lit room. That's okay. Any measurement process necessarily has some noise associated with it. But here, cleverly placed in the center of the circle is something that looks like it might be real. So that's a supernova candidate. My job on both teams as an optical spectroscopist, someone who sits around with a prism and, you know, looks at the light that's spread out into a rainbow, and I have access through the University of California to the two biggest telescopes in the world in Hawaii. I was the spectroscopist who would confirm that these were exploding stars of the right type, type 1a, and then also get the redshift of the object. So that was really great. So here's the punchline. Here are 3 of these confirmed supernovae, and the punchline is they're faint. They're very, very faint. Here, you can't even really see the galaxy before the supernova exploded. You just see the supernova. And so you say, well, okay, fine, they're distant. They're really faint. You know, why are you surprised that they're so faint? Well, they're fainter than they had any right to be. They're farther away than they had any right to be in a well-behaved universe. So let's take the following analogies. Let's suppose the universe is 1 second old. I toss this apple, and I measure its distance from my hand after 1 second. It's some distance, right? But it's been slowing down. So if Earth's mass were less, and I were to toss the apple, it wouldn't slow down as much. I can't make Earth's mass less, but I can do the next best thing. I can throw the apple faster, and in 1 second it goes higher, okay? Now remove Earth completely, and forgetting about the sun and Jupiter and all that. If I were to toss this apple, those of you physics students here, would it have any reason to slow down? No, because there's no force acting upon it. So it would get to an even greater distance in 1 second, right? Well, what we found was that the apples, the supernovae, the galaxies in which they're located, were farther away than they could have gotten, even had they not been slowing down at all, right? So it's like the apple sped up. And you could do that if you have a rocket attached to it, whoosh, like that. It speeds up. I mean, that's why you speed. I'm not suggesting you should speed on the highway, but you're late to somewhere and you speed up and you get there faster, okay? Now, you might say, well, you know, you assume the universe was 1 second old. Suppose it were 2 seconds old. Then obviously the apple got farther away. If that's what you were thinking, good job. You've got good gears, you know, turning in your head. And if you weren't thinking that, I'm not implying you don't have good gears working in your... I'm just giving kudos to those who happen to, in a split second, come up with this time argument. Very good, but it turns out that the argument is independent of the assumed age of the universe. Regardless of the assumed age of the universe, the apples are too far away, okay? So unless something else is going on, like fog in the way that makes things look dimmer, and we have to consider all that kinds of stuff, the obvious then conclusion is that the universe is accelerating. And I actually had the privilege of being the first to announce this to the world at a meeting in Los Angeles in February of 1998. I was supposed to announce only just our progress without any definitive result, because we weren't really ready to announce it. But a very savvy reporter who got a PhD in astrophysics from Princeton had talked to enough of the members of both teams that he had pieced together what our results were. And he called me up, he said, Alex, if you don't announce this, he will. And so you remember the phone call, Nick? I said, I've got to announce it, because you don't want some reporter. I like the guy, Jim Glantz, but you know, he wants to have the big story, the first story on the accelerating expansion of the universe. And so my teammates grudgingly allowed me to announce this because I was the designated speaker at that otherwise boring conference that no one wanted to go to. Okay, so astronomers see a cosmic anti-gravity force at work. We use this term anti-gravity hesitantly because people say, well, this stuff, whatever it is, you know, okay. Can we attach it to our cars and levitate over traffic jams? And the point is you cannot. It's either a property of space that can't be harnessed, or it's energy flowing through space, but there's so little of it that you're really never going to harness it. So you're not going to levitate over traffic jams. But it does have an anti-gravitating type effect. And Einstein actually predicted that there might be something in nature that produces an anti-gravitating effect. In 1917, he suggested that, but that was because he thought the universe was static, neither expanding nor collapsing. Once Hubble discovered that the universe is expanding, the whole physical and philosophical basis for something that's anti-gravitating vanished. And Einstein renounced it as having been the biggest blunder of his career. He could have been famous had he not introduced this crazy idea. So here he is, sad that he had ever introduced it. Imagine what his reaction might be if he were alive now to hear that we have resuscitated his idea of a potential repulsive force or energy in the universe. It might be something like this, right? This is not a doctored photo. This is a true photo of Einstein. Okay. So, again, you know, a lot of cartoonists and reporters get this wrong. The universe is expanding at an accelerated rate. That should be good for housing starts. I don't think so, Ram. You've dealt with real estate and housing. I don't think you can use this accelerating universe to help out your business. But anyway, the universe is expanding faster than ever, and I don't even feel a breeze. Again, it's not expanding here, and it's not accelerating here. So, okay. Well, we don't know what the stuff is that's causing the acceleration. It might be something similar to what Einstein thought of, which was really essentially an energy associated with space itself. Or it could be some new energy like light going through this room, but not light. Light doesn't have the right properties. But there's a subtle difference between an energy associated with space itself versus stuff going through space. Okay, and so those are the two generic ideas, but we call it dark energy. And through many studies, complementary studies, we now know that the dark energy is actually 70% of the cosmic pie, all that there is. You take matter and energy, and through E equals mc squared, you know, there's sort of an equivalence between them. 70% of all that there is dark energy. Not the stuff in this room. It's mostly out there. Even the dark matter, which is 25%, is mostly not in this room. It's spread out much more uniformly than Earth and our solar system and our galaxy. Less uniformly than the dark energy, but still, it's way out there. Averaged over the whole universe, the stuff of which we are made is only 5%. And the stuff that's easily visible is only about 0.5%, the stuff that's in the form of stars and stuff, okay? So this is not your mother's universe. This is very, very different. Well, the dark matter we've known about for a while now, and even the dark energy we've known about for 24 years. So for the youngest here, are there any 1 or 2-year-olds? This might be your mother's universe, but this is not your grandmother's universe, okay, for sure. All right? It's very weird. And the physical origin of this dark energy is a huge mystery. We really don't know what it is, other than these two general ideas that I gave you. In a sense, it might be arguably the most important observationally motivated problem in all of physics today. 70% of the universe, you know, what could get bigger? And it may provide clues to this holy grail of theoretical physics to unify the two great pillars of modern physics: general relativity, the theory of the very large, and quantum physics, the theory of the very small. They work beautifully in their own domains of applicability, but when you bring them together, they're at war with one another. This is clearly a quantum phenomenon that exerts an influence on the overall universe. Okay, so any quantum theory of gravity that doesn't include it can't be correct. All right, so by 2011, the evidence was so great that the discovery was honored with the Nobel Prize in Physics. It goes to, at most, 3 people. Unfortunately, Saul Perlmutter was the leader of one of the projects. Brian Schmidt and Nick were the leader of the other project. So, you know, Nick, I wasn't part of the decision. You'll forgive me, right? Nick deserved a Nobel Prize as well, but the third slot went to Adam Rees, who was a young postdoctoral scholar working with me and with the HI-Z team at Berkeley at the time of this discovery. Indeed, he was the first person on the HI-Z team to realize what the data were trying to tell us. And the first person on Saul's team passed away in 2010, and so he was ineligible, and the prize never goes to more than 3 people. But these gentlemen understood that without the rest of us working in the trenches, the discovery would never have been made, and really it was a Nobel Prize in honor of that discovery, not just the 3 people. And so they invited us to participate in Nobel Week. It was just so much fun. Here's the awarding of the Nobel Prize there. Here's a team photo that Nick had the wherewithal to just, he gave a camera to someone and he said, here, take a picture of us. And so that was really great. There's the whole HI-Z team right after the awarding of the prize. Here's the Supernova Cosmology Project. I'm not in that photo. I should be, but that's because there was very little free time during Nobel Week. And the other team was having its meeting at the same time as the HI-Z team, with which I was most affiliated, was having its celebratory lunch. And there, my wife, Noelle, revealed and gave the consolation prize to all of us who did not technically win the Nobel Prize. It was this T-shirt, Dark Energy is the New Black, a limited edition. She sent one to the King of Sweden with a note saying, Your Royal Highness, or however she referred to him, here are 2 items you are unlikely to have. A US $2 bill, which are not much in circulation, so they're kind of neat, and this T-shirt. She never got a reply, but that's because she sent the package anonymously. Now, who does that? My wife does these kinds of things. She just likes being kind anonymously. But anyway, some years later, all of us actually got recognized with the 2015 Breakthrough Prize in Fundamental Physics, established by Yuri Milner, and he's brought in Mark Zuckerberg and other people. They want to highlight the contributions of scientists in the way that movie stars and rock stars and athletes get celebrated, and they feel that scientists and physicists in particular are not celebrated enough. So it was, they recognized all of us, which was very nice. But really, the real reward was doing the science and coming up with the discovery. As a kid, I wanted to become a scientist, and never in my wildest dreams did I think that I would be associated with such a fundamental discovery. I was hoping, along with other scientists, to make some contribution to science, that would be helpful, and someday someone like Newton or Einstein would assimilate all the information and make some fundamental breakthrough. But you can't plan on being in the right place at the right time like this. So that was the real reward. Okay, in the last couple of minutes, because I want to leave time for questions, a fundamental question that may help us answer what this dark energy is whether its density, its mass per unit volume, is changing with time, okay? If it's not changing with time, then it's consistent with, or then the preferred explanation is that it's an energy associated with space itself. And if it is changing it with time, then it's some weird energy flying around through space. For many years now, the data have been consistent with it not changing density, okay, thus being this stuff associated with space itself, but we're not sure. And one way to try to resolve this issue is by measuring the current expansion rate really, really carefully. If you measure the current expansion rate really carefully, then, plus if in addition you know the history pretty well, then you can predict the future. And for example, it could get stronger, this dark energy, and eventually rip clusters of galaxies apart, and then galaxies, and then planetary systems, and then planets and stars, and then us, and then the very atoms of which you are made. That's the big rip. Most of us don't think that's what's going to happen, but it's possible. That would be the big rip-off, I suppose. But don't worry, be happy. If it does happen, it won't happen for trillions of years. I tell my students, certainly not before the final exam for my course. And so, okay. So we've been measuring this for 15 or 17 years now, and our most recent surprise, which we just got accepted for publication a couple of weeks ago, is the following. The current rate of expansion is higher than expected. Okay, wait. Higher than expected. Yeah, I just told you that we're in an accelerating universe. Take the known acceleration into account, okay, and predict what the current rate should be. Based on what initial assumptions? Based on measurements that I won't go into in detail, but suffice it to say that radio astronomers can take a picture of the universe when it was very young, only 380,000 years old. And from these little freckles, they can then, using the standard model of cosmology, where you just assume that the energy is an energy of space, because the data have been consistent with that, take it to be the energy of space, start with these little freckles, and predict what the current expansion rate should be. So I'm going to give you one quantitative thing here. All right, here's this pi. That's what they're assuming. They make a measurement of those freckles. They assume constant dark energy. And the most recent such measurements have been made by a spacecraft called Planck, after Max Planck. They predict this current expansion rate, and it's known as the Hubble parameter. Sometimes the Hubble constant, but it's not really constant. So the Hubble parameter. Okay, so we can then go off and actually measure the local Hubble parameter, and then compare it with this prediction. And the measurements are made with the Hubble Space Telescope and with the Keck telescope. And here is the surprising new result. Don't worry about the units, but just look at the number and its uncertainty. We measure this Hubble parameter to be 73.04 plus or minus 1.04 in some crazy units, okay? The Planck satellite prediction is 67.4 plus or minus 0.5, okay? Those differ. And those of you who are good at statistics will realize, if you do some calculations, they differ at the 5 standard deviation level, which means there's only a chance in 2 million that this is just the same number, but we're getting different, results just by accident like this. Because of statistics. It's like you're counting raindrops in a square meter. Not every square meter is going to have exactly the same number of raindrops. There's some fluctuation, okay? If you're standing on a square meter that only got 3 raindrops and the typical one got 100, there's probably an umbrella over you, right? It's probably not a statistical variation in the number of raindrops. That's what I'm trying to tell you. There's probably something in the physics of the universe going on here, all right? And other independent methods now support this conclusion, and that's very important in science. The more important your discovery, the more crucial it is to have independent methods that confirm your discovery. So possible explanations, maybe we or the Planck people are wrong just in our data analysis, but I don't think so, because there are now many local measurements of the Hubble constant, and they're all about the same. So, could general relativity be wrong? Maybe, but boy, that would be pretty astonishing, Could dark matter be behaving weirdly, interacting with light in some weird way? Given that we don't know what dark matter is, maybe. Could dark energy be becoming stronger and we will be ripped apart? Maybe, but I don't think so based on other evidence. Could there have been early dark energy that, in a sense, gave the universe a boost? This isn't quite the right analogy, but suppose you're watching a kid's soccer game and the ball goes zipping by at a speed greater than the speed that any one kid could have kicked. Well, you could say, well, unbeknownst to you, another kid kicked it first, and then the second kid kicked it, and that's why it has a bigger speed. So if there was some early dark energy that expanded the universe faster, and we didn't take that into account, that could be the issue. There could be some new very light subatomic particle that affects the early expansion of the universe. Basically, who knows? And I would say stay tuned. This is a very interesting question. But to summarize, this is why I'm saying we don't know how the universe will end, because there could be a big rip. For all we know, the dark energy might someday become gravitationally attractive and the apple will fall back down. We've done more research and now it's muddied the waters a little bit. But if the dark energy remains repulsive, and you want to look at a galaxy through a telescope with your very own eyes, you should come to campus here or elsewhere and do it pretty soon, in the next few tens of billions of years, because beyond that time, all the other galaxies will be whisked away to distances from which you cannot see them, and we will live in a cold, dark universe. Robert Frost could not have known any of this cosmology when he wrote his poem, Fire and Ice, in 1923, but it's remarkably appropriate given today's topic. Some say the world will end in fire. Some say in ice. From what I've tasted of desire, I hold with those who favor fire. But if it had to perish twice, I think I know enough of hate to say that for destruction, ice is also great and would suffice. So you see, Robert Frost would prefer the recollapsing universe, dying passionately in fire. But if the universe and he had to perish twice, then eternal expansion and an ending in ice would be okay with him, and that's perhaps appropriate given his name, Robert Frost. Thank you so much. I've received a lot of support from various organizations and individuals and foundations, and I'm very, very happy to answer questions. The other thing I wanted to say is that I was told if I have a book or whatever lectures to bring them with me. I brought a suitcase full of books and sky watching lectures. There's not many, but I'll be happy to autograph sheets of paper or these things after the Q&A session. So thank you very much. That'll be right over there. Okay.
Thank you, Alex, for a wonderful talk. I don't know if there are going to be any questions. I mean, it's so well, but
there's got to be
questions. Quite a few. So
all right.
I'll let you choose
excellent.
People.
How about we'll start right here, and I'll repeat the question.
Now we know that the Hubble constant has changed.
Yeah.
So does that change the life of the universe?
Yeah, so the question is, if the Hubble constant has changed, it's not really constant, does that change what we think about the age of the universe? Indeed. First of all, this Hubble constant, why I prefer to call it the Hubble parameter, is that even in standard cosmologies without dark energy, the Hubble constant actually changes with time. So it's not constant. It's constant only in the sense that at a given time, it's thought to be the same value everywhere in the universe, okay? But it can and does change with time. Now that we think it's 73 versus 67, yeah. You read in the newspapers that the universe is 13.8 billion years old. Our preferred value is 12.9. In case that makes a difference when planning which party to attend or other social gathering, know that it's only 12.9 billion years old. Okay. How about way in the back right there?
Let me just,
why don't you do it? Yeah.
No, let me just step in and saying that if you wait here till the end of the questions, we're actually going to throw T-shirts out into the audience.
Oh yeah,
so
that too.
All
right.
Free T-shirt.
Very good. Okay, way in the corner right there. Yes.
Yes, sir. So, if I understood correctly, you said you're fairly confident that the density of dark energy is consistent. Is there any reason to believe that it's evenly distributed?
Yeah. So the question is, I stated that I think that the density of the dark energy is constant. A very interesting question. Is there any reason to think that its distribution is uniform? Great question. The distribution of dark matter is really quite non-uniform. Indeed, galaxies form like the snowy peaks of a mountain chain. You've got this backbone, especially if you fly in late spring or early summer, you see this big old huge mountain range, but only the little galaxy, only the little snow-covered peaks. That's the way galaxies are on the distribution of dark matter. The distribution of dark energy is observationally pretty, we know it's at least pretty uniform, and that's because we get the same answers no matter where we look in the universe, which direction we look, and so we think it's pretty uniform. Plus, theoretically, if it were an energy associated with space itself, or even, like light flying through, but a different sort of energy, it's the kind of energy that would be pretty uniformly distributed everywhere. But certainly we need to test that hypothesis. Okay, let's see. How about, okay, we'll do it there, and then I'll come back here, and then there. I want to get a youngster. You, yes, go ahead.
The known universe.
The known universe.
Who says that's the known universe?
Who says that's the known universe? Well, I did say that we can see out to a certain distance. Basically, the distance light could have traveled in the amount of time the universe has existed. We have very good theoretical reasons and even some observational reasons to think that the universe extends beyond the parts we can see. So this is simply what we call the known universe. There could well be other universes in what we now call a multiverse, in some bigger hyperspace. That's actually quite a reasonable theoretical expectation. The problem is that theoretical expectation, though based on the physics we know, it's not just, we wake up at 3 in the morning to go to the restroom and say, let there be a multiverse. The arguments are better than that. But we have no way of testing right now for the presence of those other universes So it's a complete hypothetical right now. But I personally am quite enamored of that idea for a number of reasons. But our observable or known universe is just the part that we can see. Let me get the youngster before I go over here. There was a youngster right, yes, right there. Go ahead. Mm-hmm.
Would dark energy last forever or would it go away?
Would dark energy do what?
Would dark energy last or would it go away eventually?
Would it go away eventually? So would it last or go away? That's the key question, really. If it's a property of space itself, it lasts with the same value forever. And the effect that has is that as the universe grows, there's more and more space. So the cumulative, you add up all the little bits of space, it actually ends up becoming stronger. Not because it's getting stronger in a cubic meter or something, but because there are more cubic meters. But if it goes away, or if it, say, changes sign, that's even more, right? If it goes away, then the universe will expand forever, but it won't accelerate forever, okay? But if it changes sign and becomes gravitationally attractive, then despite the current acceleration, it's still conceivable that the stuff will someday bring the universe to a gnab-gib. And so to answer these questions, that's why we're trying to make these measurements, to see really, that was a great question. You're a budding young astrophysicist. And by the way, a special pleasure of mine today was that there's a student here, Eric Comstock. I hope I don't embarrass you, Eric, if you're here somewhere. But yeah, his parents actually brought him to see me in Berkeley when he was 5 years old, and now he's 16 and a senior here at Texas A&M University. So Eric, fantastic. So you youngsters here, keep asking the kinds of questions that Eric asked. You look like you're a little bit older than 5, but not much older. How old are you? 11. Okay, I can't see very well from way over here. I did not mean to imply that you look like you're 5 years old. But are there any 5-year-olds here? There might be. But anyway, youngsters, it's sort of what I said earlier. If someone tells you there's nothing left in physics or astrophysics to figure out, you tell them, what about the origin and nature of not just 25% of the universe, but 95% of the universe, okay? And I think I mentioned that 5% is normal matter. Only 0.5% is easily visible normal matter. Turns out there's 4.5%, I forgot to mention that, that's not easily visible normal matter, but we still know what it is. But 95% of the universe is stuff we don't understand. So there's plenty for you to do. Yes, in the red there.
Earlier you had mentioned like light years and how many...
Light years.
Light years.
Right.
At what point would people on Earth start aging faster than we would out in space?
Oh, okay. So the question is, at what point would people on Earth start aging faster than in space? Okay. So this gets to the heart of relativity, all right? Now, it turns out that in your own frame of reference, your aging never changes. Whatever your lifetime is, you'll read whatever number of books you read, watch movies, go to parties, okay? But people in motion relative to you, or in different gravitational fields, will have clocks that are going at a different rate relative to yours. And how many of you saw the movie Interstellar, okay? I'm not going to give away the punchline. Well, I will, but it's been 8 or 9 years, so if you haven't seen it yet, you're not in a great hurry to see it, right? But there's Miller's planet that goes around Gargantua, right? That supermassive black hole. We think there are supermassive black holes in the centers of most big galaxies. 1 hour on Miller's planet corresponds to 7 years on Earth. So the astronauts are desperately trying to finish they're trying to understand quantum gravity is what they're trying to do in order to, protect themselves from the blight on Earth. Exactly how, I never quite understood, but whatever. Okay, there's creative license in that movie, but Kip Thorne and others tried to make it very scientifically accurate. Anyway, they had to get their job done quickly on Miller's planet so that the astronaut could come back home before his daughter, who was like 7 or 9 or 11 when he left Earth, is still alive. And indeed, she was like 97 when he came back. So their journey only took a couple of hours, their work near the black hole. Okay? So that's a strong gravitational field. Time goes slowly relative to Earth. Similar to, if there's something zooming by you, you think its clocks are going slowly. So the way in which this is applicable to GPS is the following. There's two effects, the special relativistic effect, but the more important one is the gravity effect, the general relativistic effect. The satellites up there are like at 3.5 Earth radii, and we're at 1 Earth radius. And so they're in a weaker gravitational field. The clocks up there run slightly faster than the clocks here. They're sending radio signals, the little gizmos up there in those satellites, to your little gizmo in your car. There's a timestamp when they were sent and when they were received. The difference in time multiplied by the speed of light gives you the distance to that satellite. Knowing the distances to at least 4 satellites simultaneously uniquely determines your location on Earth. Well, that wouldn't work if the engineers had not taken into account the fact that the clocks up there are running faster than the clocks down here. The simple difference in time multiplied by the speed of light would give you the wrong distance. But they correct for that effect. So there you go, GPS. So you'll never live any longer. But I read this 400-page book I was telling Ram. 400 pages, really scholarly and all that. But here was the bottom line. To live a long time, well, have good genes, okay, but you can't do anything about that. You know, sleep enough, exercise, okay, eat the right things, be social, yeah, that turns out to be an important thing, and stimulate your brain, okay, so that's 400 pages of this book called Successful Aging, and I'm getting up there in years, so now I read books like Successful Aging, okay, so, yeah, let's see, yeah, how about right here, yes.
Basically, we assume that since dark energy is part of space, so the density of dark energy wouldn't change as the universe gets bigger, right?
Yeah, so, okay, yeah, the question, I know what you're leading to. The young man is saying the density of dark energy is not changing, because I said it's constant. But the universe is growing, so you're having more and more dark energy, right? Yeah. Is that what you're leading to?
Yeah, so, but basically the law of thermodynamics says energy can be created.
Yeah, the law, every physics student learns about conservation of energy, energy plus mass, but whatever. It can't be changed. Okay. So there are two answers, okay? The answer I like is the following. The answer I don't like is the following, okay? That energy conservation, in fact, is not necessary in general relativity, okay? And some of my colleagues say that it's not a question. Energy conservation is not a big deal. But I like energy to be conserved. I kind of like conservation of energy. I don't know. Igor, what do you think? Is energy conserved in general relativity? Yeah, okay. So here's how you can answer that question. And Ram and I went on a run this morning, and he asked that same question. You get more dark energy, and it's a positive energy density, okay? But there's a thing associated with it called a negative pressure, and that's what actually accelerates the universe, okay? But the positive energy density actually has an attractive component, and that has a negative gravitational potential energy associated with it. And the amount of negative potential energy created as you're expanding the universe exactly balances the amount of dark energy that's produced. In a way similar to this apple. When I drop it, it has zero kinetic energy in this frame of reference, and I could call the potential energy 0. I can call it anything I want, pi or 16 or 42. The answer to the question of life, the universe, and everything. Some of you laughed, so you got my drift there. But as I drop it, it picks up 1, 2, 3, 4, 5 units of kinetic energy, but also negative 1, 2, 3, 4, 5 units of potential energy. Okay, so it balances, and indeed. What we mean by potential energy is that I did work on this apple to get it up here. It can do work back for me by, hitting some windmill or an apple mill or something like that. So the great thing about both the inflating universe, which is how we think our universe became really, really big, and today's dark energy is that they actually do conserve energy, despite looking initially like they totally violate this most basic dictum in physics, all right? Yeah, okay, back there in Texas, sure, yeah. Yeah, so the question is, as the universe is expanding, is it releasing more energy as it's expanding? It's not releasing energy to other dimensions, right? You think of it as a balloon or something, and there's the rubber of the balloon. But let's say your universe is that hypothetical universe. It's just the balloon. Inside and outside are a different dimension, but that's not part of the universe to which you have access. So we don't think our universe is emitting energy to other dimensions, with the possible exception of the particles that are theorized to carry gravity. In Einstein's theory, gravity is a curvature of space-time, but in what's called a quantum field theory, as with electromagnetism or any other of the major forces in physics, the forces are carried by quanta. And in string theory and in this thing called brane theory, the quanta, the little particles of gravity called gravitons actually can go out of the universe into some other dimension. But in general, let's forget about that possibility. So in this expanding universe filled with dark energy, the energy pervades the known dimensions. And so the universe isn't emitting into any other dimension, okay? It's creating more energy within the dimensions of this expanding balloon. But that doesn't violate conservation of energy, and even if it does, according to some general relativists, that's okay. All right? Does that kind of answer your question? Okay, great. How about, gosh, I mean, there's so many. How about way over there? Yes, with the, you did something to your hand, so I'm sorry for that.
Are there other possibilities of how the universe will end? And if so, how did you rule down the two?
Yeah, are there other possibilities to how the universe will end? And if so, how do we rule them out? So without the dark energy, I gave you the two possibilities of, recollapse and then easy expansion forever. There's a boundary where if I were to toss this apple at exactly the escape speed, then it would keep on going away forever, but it would approach zero speed as time approaches infinity. So it would never become negative, it would never come back to us, but it wouldn't expand forever with a positive energy either. It would be the dividing line. And that's like an apple thrown at exactly the escape speed. For a long time, theorists preferred that kind of a universe. It requires a certain average density of normal matter and normal energy in space. Okay, we'll call it 1. All right? And for a long time, the observers were saying, well, the density is only 0.3, and so the universe will easily expand forever, okay, instead of just barely expanding forever. But these theorists said, well, we have reasons for thinking that the density is actually 1, and you'll have this perfectly balanced universe that just barely expands forever. Now we've found that when you include the dark energy, the overall density is 1. Unfortunately, for those who would like the universe to come to a standstill at time equals infinity, the dark energy has the wrong effect. It's accelerating the expansion of the universe. So if that remains the case, then that's the future of the universe. But it's conceivable that the dark energy will become attractive. And if that total is sufficiently close to 1, when you add all of it together, overall then, in trillions and quadrillions of years, that universe would indeed approach one whose speed tends towards 0 as time tends toward infinity. But you'd need the current dark energy to become attractive rather than repulsive. And that's not out of the question, okay? And we've measured this density parameter to be darn close to 1. So if it does someday become the case that dark energy becomes attractive rather than repulsive, then already we're actually kind of at this happy, I don't know if you're happy or sad, but in this situation where the universe will just barely expand forever. But if I were a betting person, which I'm not in general, I don't know about Nick, I'm betting that the dark energy will remain repulsive and that the universe will keep on expanding faster and faster with time.
Alex, we're going to have to
yeah, I understand.
Let's
right.
take one question each from each one of the 3
Oh,
sections.
that
Start in this section over here.
I don't want to be the person who chooses them, so I'll let you choose the final 3 questioners.
Thanks, Alex.
How about the youngster there?
Yes,
yeah,
please go ahead.
You've got Maxwell's equations on your do you? Right? What do you have on your T-shirt? Oh, you have a Lagrangian. Very good. How old are you? 10. You've got Lagrangians on your T-shirt. Do you know what they mean? Okay, you will. You will one of these years. Keep studying physics, okay? Anyway, what's your question?
My question is, how do dark matter and dark energy affect each other?
How do dark matter and dark energy affect each other? Great question. So, since we don't know what either of them is, my honest answer is we don't know. But we think they're very different. They're not just the two sides of a coin, right? And by the way, sometimes people say, well, we know E equals mc squared, so are dark matter and dark energy transformable into one another? The current state of understanding is that probably not. They're probably very separate types of things and probably don't even affect each other than in their overall effect on the structure and evolution of the universe. But you definitely, we think, can't just use E equals mc squared to turn dark matter into dark energy or vice versa. Yeah. Look at all these questions. Holy moly. You're really on the spot here, Nick.
Well, this little girl in the red T-shirt.
Okay.
Black holes, when they bend, like the it bends.
Yeah. I'll repeat this.
Does dark energy and dark mass do the same thing?
Right. So the point being made is that black holes and other things, they bend space and time. And in fact, a black hole bends it so much that the light can't get out. And so the question is, do dark matter and dark energy bend space and time? And the answer is yes, indeed. Indeed, there's this one thing I was talking about. There's just enough dark matter and dark energy to change the overall shape of the universe to something that mathematically has what's called negative curvature. The closest analogy I can give you is a horse's saddle, all right? That has some of the desired properties. But the tendency of empty space is to be like a horse's saddle, negatively curved. But there's just enough dark matter and dark energy and normal matter to make it flat. And by that we mean Euclidean. And so you may have learned, or you someday will learn, that no matter which triangle you draw, the sum of the interior angles is 180 degrees, okay? That's a property of what we call flat space. And we've measured giant triangles in the sky, so we know that away from black holes and stars and stuff, the average distribution of matter and energy of the universe makes it flat. And if there were more, then it makes it positively curved and it becomes more or less like a sphere. So yes, dark matter and dark energy have that effect on space and time. Yeah.
So before you take the last question.
Oh, yes, right.
We're going to have you throw out the T-shirts.
Okay, I'm going to throw out the T-shirts.
Okay, so we'll bring them here. And then
okay.
After that, you're going to be over at the table here.
Yes, I'll be there. And I can answer more questions and, sign sheets of paper, sign books or whatever.
And get his autograph if you wish.
Yeah, right, yeah. So
one more
okay.
here.
So we're going to do this question and then stick around. We're going to throw the T-shirts, okay. Right? Okay.
Okay. As discovery of Higgs boson and it challenges our way of the elementary school of particles, has that in any way changed your mind on, or changed your perspective on dark energy?
Yeah. The question is this Higgs particle that was discovered a decade ago at the Large Hadron Collider, in fact, in 2012. Has that changed our view of any of the stuff we're talking about here? Indeed, it's quite relevant. There's this Higgs field that is, sort of permeates all of space. And little knots or vibrations in the field are the particles, and they're easier to find, than the field itself. Okay, it's sort of like, in general, little bunches of energy in a field are easier to find than a uniformly distributed field itself. So the Higgs particles, the Higgs bosons have been found that strongly suggest that the Higgs field is a real thing. The dark energy that we're talking about is a Higgs field. It's just not the Higgs field that is thought to give mass to particles. And I forgot to say that why do people care about the Higgs field? Different particles zipping through the Higgs field feel different amounts of resistance, like viscosity. If this were a vacuum, it'd be easy for me to take my finger through it. With air, it's not much harder. Water, it would be harder. Molasses, even harder. So different particles acquire mass depending on how much resistance they feel to this Higgs field. And photons don't acquire any mass because they don't care that the field is there, all right? So if that sounded complicated, there's a joke that illustrates beautifully what the Higgs field is all about and what the Higgs particle is. Okay, so a Higgs particle walks into a Catholic church, and the priest says, what are you doing here? Get out of here. We don't want you. And the Higgs particle says, but you can't have mass without me. Okay, so there you go. That is the Higgs field and the Higgs particle. Okay, so Higgs fields are, there are many kinds of energy fields that basically can pervade space. And you can think of both the dark energy and the stuff that inflated the universe, we think. I didn't talk about that, but that's how we think the universe grew very big. Something like that sounds very attractive to many of us. Those were all Higgs fields, but not the Higgs field. But the fact that they found the Higgs particle, which is presumably associated with the Higgs field, suggests that indeed these are not such crazy ideas to have new forms of new types of fields which are different from electromagnetism or even, what's called the strong nuclear force or the weak nuclear force or the gravitational thing. There are other interesting fields. And indeed, to understand the standard model of particle physics, there are sort of 3 families, 4 particles for each family, and then there are the little force-carrying thingies. There's like 20 such things. But the one missing one, there was a square, a pigeonhole that had not yet been filled. And if it didn't get filled, the whole theory would go crumbling down. That was the Higgs particle. And so it was a momentous event when the Higgs particle was found. But it also suggests that we might be on the right track with these other things. But it does not, I would say, to be fair, directly imply that we're right with all this dark energy. I will finish simply by saying, illustrating exercising some humility. I do wake up sometimes in the middle of the night, my wife will attest to this, screaming that dark matter and dark energy are just completely wrong. We're just completely wrong. And they are our modern day Ptolemaic epicycles. In just 23 seconds, Aristotle had, an earth-centered theory of the universe. And Ptolemy figured out calculational tools to better predict where and explain where the planets are than Aristotle was able to do. And he had, things going around little epicycles, and then the whole thing would go around Earth, and you could explain the backwards motion of planets every year and blah, 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 blah. It was a wonderful calculational tool. It lasted 1,500 years. Astrologers were very grateful to Ptolemy because they had to predict when it was a propitious time for queens and kings to have children and all this kind of stuff. Even if slight variations had been seen from the predictions, Ptolemy could have added epicycles to epicycles. Indeed, those of you who have studied advanced mathematics will recognize that Ptolemy was the original Fourier. It was a Fourier series if you just added more of these things, epicycles upon epicycles. It could explain the observed positions of planets with arbitrary precision. But other observations later showed it was wrong. Earth goes around the sun. They actually go around their common center of mass, but Earth moves a hell of a lot more than the sun does, okay? So it was just wrong. But he wasn't a stupid guy. He was a brilliant guy, and mathematically he came up with all this stuff. What if today's dark matter and dark energy are completely wrong, like the epicycles were? It is a possibility, and maybe one of the youngsters here will figure that out. Nick and I are too old. I hope that's okay with me. We're not going to figure it out. It's going to take 30 or 40 years of someone who has a fresh new world view. And often theoretical physicists and mathematicians, not that they're done after age 30 or 40, but they do a lot of their greatest work in their 20s, actually, because they know enough to know what other people have learned, but they're not already set in their ways and stuff. So they have, crazy ideas, some of which are not so crazy. So great final question.
Okay, well, let's give Alex a big round of applause. Thank you.
All right.
Let's go over a couple of things over there.
Okay. All right. So this is great. So
Nick's going to take some to the
I have a chance to make many friends and many enemies here. Yeah, I'll start here, but don't worry, you won't be discriminated against in that third of the room. Right? There's what, 1, 2, 3 thirds. Okay, very good. So here we go. Here we go. All right, look at this. Look at this. All right, this is so much fun. Okay. They're so enthusiastic. I'm going to get one to them over there. Okay. Yeah, pardon? Okay, now let's go over here. And here. There you go. And over there. And over there. And here you go. Oh, you got that cooler Ronaldinho shirt. And so that's those ones. Now do we do the middle third? Okay, now we do the middle third. Look at that. All right. These people, Texas A&M t-shirts. All right. Here we go. Okay, so we'll start right here. We'll start right there. We'll go farther out. We'll go even farther out. Thank you very much. This side here. Let's see. Here. There we go. All right, great. There you go. Look at all these t-shirts. Look at all these t-shirts. All right, there we go. Okay, all right. Okay, all the shirts out there. And then, last, but definitely not least, last time I started here in the front, this time we'll start here in the back. I haven't had this much fun in a long time. All right. How much fun is this? Over there. One more. Oh, good. All right. Oh, good. I guess I heard one more. Again, hope you enjoy your day. Yes, of course. Yeah, absolutely. Here, let me take off. Here's this thing. Yeah, okay, here we go. All right. Excellent. Okay, very good. Let me head over to here, and then I can talk to additional people. Yeah. Okay. Go over this way.
Thank you so much for celebrating the wonders of science with us today. If you liked what you saw today, please hit that subscribe button as we will continue to release more awesome content free for everybody to enjoy. We also have other popular channels like TikTok, Instagram, Facebook, and Twitter, where we post about science all of the time. There are links for that in the video description below. It's finally time to say farewell. We hope to see you all next year. Goodbye, friends, and gig 'em.